Hello there and welcome to Science for Sleep, where curiosity settles in quietly for the evening and the universe slows down just enough for us to wander through it together. Tonight, we're going to drift into a mystery hidden inside the galaxy we call home, not a mystery about aliens or exploding planets or anything quite so dramatic, although to be fair, the Milky Way has plenty of those lying around. No, this one is stranger in a quieter sort of way, because astronomers have discovered that enormous regions of our galaxy are far hotter than they should be, while other regions remain comparatively calm and cool, as though the Milky Way itself has developed an uneven fever. Which raises a rather uncomfortable question. Why would half of an entire galaxy be hotter than the rest? Now, when we picture the Milky Way, most of us imagine something peaceful, a soft river of stars stretching across a dark sky, a calm spiral drifting silently through space. Maybe something seen from a campsite far away from city lights, where the sky suddenly becomes crowded with more stars than you realized existed. It feels still, balanced, almost sleepy. But galaxies are not calm places. Underneath that quiet appearance is an environment full of violent radiation, magnetic storms, exploding stars, invisible particles moving near the speed of light, and giant clouds of gas heated to temperatures so extreme they would vaporize anything humans have ever built long before it got close enough to complain about it. And somewhere inside all of that chaos, astronomers started noticing something odd. One side of the Milky Way seemed different, hotter, more energetic, more turbulent. Not slightly hotter either. Massive regions above and below the galactic center glow with high-energy radiation. Certain clouds of gas are heated far beyond what normal starlight should accomplish. Strange structures stretch tens of thousands of light-years through space like scars left behind by ancient violence. Even the invisible halo surrounding our galaxy appears uneven in temperature. It is, in the gentlest possible scientific terms, a bit suspicious. Before we untangle any of that though, I'd love to ask you something. Where are you listening from tonight? And what time is it in your little corner of Earth right now? Maybe it's late evening where you are. Maybe rain is tapping softly against the window. Perhaps you're listening under blankets while your phone slowly slides toward your face 1 inch at a time, as all phones eventually do during nighttime videos. If so, I wish you luck in the ongoing battle against gravity. And if this quiet journey through the hotter half of the Milky Way helps you relax, unwind, or simply drift away from the noise of the day for a little while, I'd be very grateful if you gave the video a like and maybe subscribed as well. It helps this small, sleepy corner of science find more fellow travellers wandering around the internet at unreasonable hours. Now then, let's settle in. Because tonight's story begins with a galaxy that does not behave quite as evenly as we once assumed. For a very long time, humans imagined the Milky Way as fairly ordinary. Vast, certainly. Beautiful, definitely. But stable, predictable. A giant rotating disk of stars spinning peacefully through the darkness. That image survived for centuries, partly because the galaxy is so unimaginably large that most changes happen far too slowly for humans to notice. Stars drift quietly over millions of years. Clouds of gas collapse over enormous stretches of time. Even catastrophic explosions become gentle when viewed from tens of thousands of light-years away. From Earth, the galaxy can look almost frozen. But appearances in astronomy are often deceptive. The moment scientists began observing the Milky Way in wavelengths beyond visible light, the galaxy started revealing a much messier personality. Radio telescopes uncovered huge invisible clouds spread across space. Infrared observatories found warm dust hidden behind dark curtains of gas. X-ray telescopes detected regions so energetic they glowed with radiation powerful enough to pass straight through ordinary matter. Gamma-ray observatories discovered colossal structures, blasting high-energy particles far above the plane of the galaxy itself. Suddenly, the Milky Way looked less like a peaceful starry spiral and more like an active machine, with parts overheating in strange places, and perhaps the strangest thing of all was that the heat wasn't distributed evenly. Certain regions appeared dramatically more energetic than others. Imagine walking into a room and discovering one wall is mysteriously warmer than the rest for no obvious reason. Maybe you'd check for a heater, or sunlight, or perhaps someone secretly installed a giant oven inside the wallpaper. Astronomers essentially found themselves in that situation, except the room was over 100,000 light-years wide. Now, when scientists talk about heat in space, they don't always mean what we normally think of as temperature. That part can get a little confusing because space itself is mostly extremely cold. The average temperature of the universe is only a few degrees above absolute zero, cold enough that atoms barely move at all. But inside galaxies, local conditions can become astonishingly extreme. Some gas clouds remain chilly enough for molecules to form peacefully in the dark. Others are heated by nearby stars until they glow brightly. Some regions contain plasma so energetic that electrons are stripped entirely from atoms and whipped around by magnetic fields at incredible speeds. And then there are places near black holes where matter becomes so hot that it radiates X-rays before disappearing forever. The Milky Way contains all of these environments at once. What puzzled astronomers was not merely that hot regions existed. That part was expected. Galaxies contain stars, after all, and stars are essentially giant nuclear furnaces suspended in space by gravity and stubbornness. The real puzzle was scale. Entire sections of the Milky Way appeared hotter, more turbulent, and more violent than neighbouring regions in ways that were difficult to explain through ordinary star formation alone. Some observations suggested enormous outflows of superheated gas rising above the galactic centre. Others hinted at ancient explosions powerful enough to reshape huge portions of the galaxy itself. High-energy particles called cosmic rays seemed concentrated unevenly across space. Even the thin halo of gas surrounding the Milky Way appeared asymmetrical in temperature and energy. It was as though the galaxy had experienced some ancient trauma and never fully settled down afterward. Naturally, astronomers became extremely interested. Astronomers become interested in many things, to be fair. If you tell a scientist there is a mysterious glowing bubble larger than entire constellations floating invisibly above the galaxy, they tend not to shrug and move on with their day. Instead, telescopes pointed toward the galactic centre, again and again, and what they found there only deepened the mystery. At the centre of the Milky Way sits Sagittarius A, the supermassive black hole around which our entire galaxy slowly rotates. It contains roughly 4 million times the mass of our Sun packed into a relatively small region of space. Now, thankfully, it is very far away from us, about 26,000 light-years away in fact, which is generally considered a comfortable distance when discussing supermassive black holes. But despite being comparatively quiet today, Sagittarius A may not always have been so calm. Evidence has emerged suggesting that millions of years ago our galactic centre may have erupted violently, releasing colossal amounts of energy into surrounding space. Not a little burst either. Something on a scale large enough to inflate gigantic structures above and below the galaxy called the Fermi bubbles, enormous lobes of high-energy radiation extending roughly 25,000 light-years in each direction. To put that into perspective, those bubbles are so large that if you could somehow see them with your naked eye, they would dominate huge portions of Earth's sky. And yet they remained invisible to humanity until gamma-ray telescopes finally revealed them in 2010. Which means that for all of recorded human history, our species lived quietly inside a galaxy containing giant hidden structures larger than civilizations could even comprehend. There is something oddly humbling about that. Actually, astronomy specializes in humility. Every time humans become slightly too confident about understanding the cosmos, the universe casually reveals another impossible structure the size of several thousand solar systems and reminds us we are tiny mammals standing on a damp rock arguing about parking spaces. Still, Little by little, scientists began piecing together clues. X-ray observations showed superheated gas flowing through parts of the galaxy. Radio emissions traced magnetic structures twisting across enormous distances. Infrared surveys uncovered turbulent star-forming regions, packed with massive young stars heating their surroundings intensely. The Milky Way, it turned out, was not thermally balanced at all. Different regions were living very different lives. Some areas remained relatively quiet, filled with older stars and cooler gas drifting peacefully through galactic suburbs. Other regions looked more like cosmic industrial zones where stars exploded regularly, magnetic fields tangled violently, and high-energy particles ricocheted through space like microscopic bullets. Even our own solar system occupies a comparatively calm neighbourhood by galactic standards, and honestly, that is probably for the best. Human civilization struggles emotionally with mildly unstable Wi-Fi. We would likely not thrive inside a dense starburst region flooded with radiation powerful enough to sterilize planets. The farther scientists looked, the more they realized the Milky Way behaves less like a static object and more like a living environment constantly changing over millions of years. Stars form. Stars die. Gas clouds collapse. Black holes feed. Magnetic fields twist. Shockwaves travel across interstellar space. And all of it contributes to an uneven galactic landscape where temperature, energy, and turbulence vary enormously depending on location. In some ways, asking why half the galaxy is hotter than the rest is a bit like asking why some parts of Earth experience hurricanes while others remain calm deserts. Large systems naturally develop regions of imbalance. Except in the Milky Way, those imbalances can span tens of thousands of light years. Now, there is another reason this mystery matters beyond simple curiosity. Heat tells astronomers where energy is moving, and energy is one of the great storytellers of the universe. Wherever gas becomes unusually hot, something caused it. Maybe stars, maybe shockwaves, maybe magnetic reconnection, maybe ancient black hole eruptions, maybe supernova explosions occurring so frequently that entire regions of space become flooded with high-energy particles. By mapping heat across the galaxy, astronomers are effectively tracing the Milky Way's hidden history, like detectives finding scorch marks after a fire. And sometimes those scorch marks suggest events far more dramatic than anyone originally expected. For example, certain observations imply that the centre of the Milky Way may have undergone periods of intense activity not very long ago in cosmic terms. The black hole at the centre could have consumed enormous amounts of matter, releasing radiation powerful enough to reshape surrounding regions. Other scientists suspect that clusters of massive stars exploding one after another may have created giant galactic winds carrying heat and particles outward into the halo surrounding the galaxy. There are even more exotic possibilities involving dark matter interactions, although astronomers become very cautious whenever dark matter enters the conversation, because it has a habit of turning simple discussions into 3-hour lectures involving invisible particles and complicated graphs. Useful for science, less useful for sleep. So tonight we'll take the gentler route through the mystery. We'll wander slowly through the structure of the Milky Way itself. We'll explore what astronomers actually mean when they talk about temperature in space. We'll visit the crowded galactic centre where stars gather densely around a sleeping giant black hole. We'll look at the enormous bubbles of radiation towering above the galaxy. We'll examine supernova explosions, cosmic rays, magnetic fields, and ancient eruptions that may still be heating regions of space long after the original events faded away. And somewhere along the way, we may begin to understand why our galaxy seems so strangely uneven. Because the Milky Way is not merely a collection of stars. It is an active environment shaped by violence, gravity, radiation, and time itself. Even now, while Earth turns quietly beneath the night sky, gigantic rivers of hot plasma drift through interstellar space. Invisible particles stream across the galaxy near light speed. Ancient shockwaves continue expanding through darkness, left behind by stars that died before humanity even existed. The galaxy never truly rests. It only appears calm from very far away. And perhaps that is one of the most comforting things about astronomy. The realization that enormous processes continue unfolding whether we notice them or not. Vast structures move patiently across millions of years while we live our small human lives beneath them. Right now, somewhere inside the Milky Way, a massive star is nearing the end of its existence. Somewhere else, cold gas is beginning to collapse into new suns, and deep near the galactic centre, invisible energies continue shaping the hotter half of our galaxy in ways astronomers are still trying to understand. Most of us grow up thinking of heat in fairly ordinary ways. A cup of tea cooling on a table, sunlight warming the pavement, a radiator hissing quietly during winter. Heat feels familiar, practical, deeply connected to everyday life. It belongs to kitchens and blankets, and the uncomfortable experience of touching a baking tray without proper emotional preparation. Space, meanwhile, seems like the opposite of heat. When people imagine outer space, they usually picture something frozen and empty. A silent black vacuum colder than Antarctica, colder than the deepest ocean, colder than that side of the bed nobody wants in winter. And technically, that picture is not entirely wrong. Much of the universe is incredibly cold. Between stars, temperatures often hover only a few degrees above absolute zero, the point where atoms possess almost no motion at all. If you floated far away from stars and galaxies into the emptiness between cosmic structures, you would encounter some of the coldest environments nature can produce. So when astronomers say that parts of the Milky Way are hotter, the obvious question becomes hotter than what exactly? And perhaps more importantly, what does hot even mean in a place where there's almost no air, no atmosphere, and in many cases barely any matter at all? As it turns out, heat in space is a surprisingly strange concept. Tonight's mystery about the hotter half of the Milky Way depends entirely on understanding that strangeness, because astronomers are not walking around the galaxy holding giant thermometers up to stars and gas clouds while making concerned facial expressions. Instead, they measure heat indirectly, using light itself, and that is where things begin to get wonderfully peculiar. You see, temperature in physics is really a measure of motion. The hotter something is, the faster its particles move. When water boils, its molecules move around energetically. When metal glows red in a furnace, its atoms vibrate intensely. Cool something down enough, and those motions slow dramatically. In daily life, we experience this through touch, because fast-moving particles transfer energy to our skin. Heat flows naturally from hotter objects to cooler ones. Your hands warm a mug, a stove heats a pan, a cat occupies the warmest available blanket with military efficiency. But space changes the rules slightly. Out there, there's often so little matter that ordinary heat transfer barely works at all. For example, if you floated in open space near Earth, you would not instantly freeze solid the way movies sometimes suggest. In fact, without air to carry heat away efficiently, you might lose body warmth surprisingly slowly in some situations. Space is cold, yes, but it is also mostly empty, and emptiness is oddly bad at conducting heat. Instead, energy moves primarily through radiation. Light carries heat. Infrared radiation from the sun warms Earth across 150 million kilometers of empty space. Stars heat surrounding gas through radiation. X-rays, ultraviolet light, gamma rays, and radio waves all transport energy through the galaxy in different ways, which means astronomers often determine temperature by studying the light emitted by objects rather than directly measuring heat itself. Different temperatures produce different forms of radiation. Cool objects emit mostly infrared light. Hotter stars produce visible light. Extremely energetic environments generate ultraviolet radiation, X-rays, or even gamma rays. In a way, the universe glows according to temperature. and once scientists learned how to read that glow properly, the Milky Way began revealing enormous hidden structures invisible to human eyes. Take our Sun, for example. Its surface temperature is about 5,500 degrees Celsius, hot enough to emit the visible light that illuminates Earth during the day. But above the visible surface lies the solar corona, an outer atmosphere somehow heated to millions of degrees. Now, this has confused scientists for decades because logically the outer layers should be cooler, not hotter. It's a little like walking away from a campfire and discovering the air 50 feet away is hotter than the flames themselves. Space enjoys behaving like that occasionally. Astronomers suspect magnetic fields play a major role in heating the corona, twisting and reconnecting in violent bursts that accelerate particles to tremendous speeds. The Sun constantly ejects hot plasma outward through the solar wind, flooding the solar system with charged particles, and our Sun is considered relatively ordinary. Elsewhere in the galaxy, things become dramatically more intense. Massive young stars burn far hotter than the Sun, producing fierce ultraviolet radiation capable of ionizing enormous clouds of gas around them. Supernova explosions briefly outshine entire galaxies. Neutron stars and black holes generate regions so energetic they radiate powerful X-rays across space. Some gas in the Milky Way reaches temperatures of millions of degrees. Not metaphorically, literally millions. At those temperatures, atoms become completely stripped apart. Electrons break free from nuclei, creating plasma, an electrically charged state of matter often called the fourth state beyond solids, liquids and gases. In fact, most visible matter in the universe exists as plasma, which means that despite how peaceful the night sky looks, much of the cosmos is actually filled with superheated electrically charged material, moving under the influence of magnetic fields and gravity. Rather energetic behavior for something humans once described as the heavens. Now here is where our mystery begins deepening. Astronomers noticed that some regions of the Milky Way contain much larger concentrations of this hot plasma than others, and not only slightly larger. Entire galactic structures glow brightly in X-rays, revealing temperatures far beyond what ordinary starlight alone should create. One particularly important discovery came from observing diffuse X-ray emission spread throughout the galactic center. Diffuse simply means spread out rather than concentrated in individual stars. Instead of seeing isolated hot objects, astronomers detected vast regions of glowing high-energy gas permeating large sections of space. This suggested something enormous had heated the surrounding environment. Perhaps many things, possibly over millions of years. To understand how strange this is, imagine entering a forest and discovering the entire air itself feels warm, even far away from individual campfires. You would immediately suspect some larger process heating the whole region. That is essentially what astronomers found near the center of the Milky Way. Huge reservoirs of hot gas, enormous energetic structures, temperatures reaching millions of degrees. And importantly, those regions appeared unevenly distributed. Some areas remained comparatively cooler and calmer. Others looked violently active. Now, when scientists say gas reaches millions of degrees in space, it's worth clarifying something before anyone imagines giant invisible ovens floating around the galaxy. Temperature in space can be misleading because density matters enormously. A tiny number of particles moving extremely fast can technically possess very high temperatures while still containing relatively little total heat energy. You could travel through certain million-degree regions of space without instantly vaporizing, because the gas there is incredibly thin, sparse enough in fact that particles might collide only occasionally. Still, from an astrophysical standpoint, those environments are astonishingly energetic. Particles moving at such speeds produce high-energy radiation detectable across enormous distances. That radiation acts like a cosmic fingerprint, allowing astronomers to map otherwise invisible structures. And once telescopes sensitive to X-rays and gamma rays became advanced enough, the Milky Way suddenly appeared full of hidden heat. One of the great surprises of modern astronomy is how incomplete visible light alone really is. Human eyes evolved under sunlight on Earth. We see only a narrow slice of the electromagnetic spectrum because that range happens to be useful for survival here. But the universe emits radiation across vastly broader wavelengths. Infrared, ultraviolet, radio waves, microwaves, X-rays, gamma rays. Different forms of light reveal different layers of reality. Visible light shows stars. Infrared exposes warm dust clouds. Radio waves trace magnetic structures and cold hydrogen gas. X-rays uncover violent high-energy regions. Gamma rays reveal the most extreme energetic processes in existence. So as astronomers expanded beyond ordinary visible observations, the Milky Way transformed from a calm, starry band into something much more complicated. It became layered, active, uneven, and deeply dynamic. For example, giant molecular clouds drifting quietly through spiral arms remain relatively cool by cosmic standards, perhaps only a few dozen degrees above absolute zero. These cold clouds are stellar nurseries where gravity slowly pulls gas together until new stars ignite. Meanwhile, nearby regions might contain blazing young stars heating surrounding gas to tens of thousands of degrees. Elsewhere, ancient supernova remnants send shockwaves racing outward through space, compressing and heating interstellar material. Magnetic turbulence accelerates cosmic rays. Black holes feed on matter and release tremendous energy. The galaxy contains weather in a sense. Not weather like Earth's rainstorms and winds, of course, although imagining a galactic weather forecast is admittedly entertaining. Tomorrow near Sagittarius A, expect scattered plasma turbulence with a high chance of radiation. Still, the analogy is useful. Galaxies possess regions of differing activity levels, energy flows and thermal conditions. Some places remain quiet for millions of years. Others erupt repeatedly with violent events, and the centre of the Milky Way appears particularly restless. Astronomers sometimes refer to the galactic centre as an extreme environment because stars are packed far more densely there than in our neighbourhood. Massive molecular clouds collide more frequently. Magnetic fields intensify. Radiation levels rise dramatically. Our solar system lives comfortably out in the galactic suburbs, orbiting the centre every 230 million years or so at a relatively safe distance. The galactic centre, meanwhile, resembles cosmic downtown traffic during rush hour. Crowded, energetic, occasionally explosive, and because energy tends to produce heat, these conditions naturally generate hotter regions. But observations suggest something even larger may be happening. Scientists discovered giant plumes and bubbles of hot gas extending far above and below the galactic plane itself. Not small local structures, enormous ones. Structures large enough to span tens of thousands of light years. These regions emit gamma rays and X-rays indicating incredibly energetic processes occurred there sometime in the past. Perhaps ancient black hole eruptions. Perhaps intense periods of star formation and supernova explosions. Possibly both. Whatever caused them released staggering amounts of energy into the surrounding galaxy, and some of that energy still lingers today as heat. Now, one subtle but important point often gets overlooked in discussions about galactic temperature. Heat in space is not evenly shared. Unlike Earth's atmosphere, where air mixes relatively efficiently, interstellar space is so diffuse that regions can remain thermally isolated for immense periods of time. Hot gas does not instantly distribute itself evenly across the galaxy. Shockwaves travel slowly on galactic scales. Magnetic fields guide particle motion unpredictably. Gravity creates barriers and flows. Radiation interacts differently depending on local density. As a result, the Milky Way develops patches of differing thermal behaviour. Some regions effectively trap heat longer than others. Others cool rapidly through radiation. Some become reheated repeatedly by nearby stellar activity. And some may preserve signatures of ancient events long after the original source disappeared. In a way, the galaxy remembers. A supernova explosion may last only briefly, but the heated gas and accelerated particles it creates can influence surrounding space for millions of years afterward. Likewise, if Sagittarius A star experienced a violent feeding episode long ago, evidence of that outburst could still remain visible today through giant hot structures permeating the galaxy. Astronomy often works like archaeology in that sense. Scientists reconstruct ancient cosmic events from lingering traces. Hot gas becomes evidence. Radiation becomes memory. Temperature maps become historical documents written across space itself, and occasionally those documents reveal stories far stranger than expected. One especially interesting clue comes from the fact that some galactic structures appear asymmetrical, not perfectly balanced around the Milky Way, more energetic on one side, more heated in particular directions. This asymmetry suggests that whatever processes shape the galaxy may not have occurred evenly. Perhaps giant outflows escaped more easily through certain regions. Perhaps magnetic fields redirected energetic particles unevenly. Perhaps past collisions with smaller galaxies disrupted gas distribution. Or perhaps multiple mechanisms overlapped over millions of years, creating the uneven thermal landscape astronomers observe today. The honest answer is that scientists still debate many details. Galaxies are extremely complicated systems. Trying to model one accurately involves gravity, magnetism, plasma physics, radiation transport, fluid dynamics, cosmic ray propagation, stellar evolution, and occasionally computers becoming emotionally exhausted halfway through the calculations. Even so, the broader picture has become increasingly clear. The Milky Way is not thermally uniform. Different regions contain dramatically different amounts of energy, and much of the hotter material appears concentrated around structures linked to the galactic center and large-scale energetic events. What makes this especially fascinating is that humans only discovered most of it recently. For almost all of history, people looked at the Milky Way with naked eyes and saw only soft, visible starlight. No X-ray glow, no gamma-ray bubbles, no hidden hot plasma, no colossal magnetic structures. Those invisible layers remained concealed until technology expanded human vision beyond ordinary sight. There is something wonderfully strange about realizing the universe always contained these enormous energetic structures, while humanity remained completely unaware of them. Ancient civilizations built myths around the Milky Way. Philosophers debated its nature. Poets described its beauty, all while giant invisible regions of million-degree plasma drifted silently overhead. The cosmos rarely feels obligated to reveal everything at once. Instead, it allows humans small glimpses piece by piece, a little more each century, and with every new wavelength we learn to observe, reality grows more complicated, sometimes hotter too. Because what astronomers mean by hot in space is not merely warmth, it is motion, energy, violence, particles accelerated across impossible distances, invisible radiation carrying evidence of ancient cosmic events, and somewhere inside all of that hidden heat lies the explanation for why half of our galaxy seems far more energetic than the rest. If you step outside on a dark enough night, far away from city lights and glowing windows and the suspiciously bright gas station that somehow remains visible from 3 counties away, the Milky Way appears almost simple. A pale band stretches across the sky, soft, dusty, calm. To ancient people, it looked like smoke, milk, mist, or a glowing river crossing the heavens. Different civilizations imagined it as a pathway for souls, a celestial road, a seam in the sky, or the spilled remains of something divine. And honestly, given what they had available at the time, those guesses were not bad at all. Because from Earth, the Milky Way does resemble a single continuous structure, but appearances in astronomy are usually lying at least a little. The truth is that the glowing band overhead is only a tiny visible slice of a much larger system, one with layers, hidden regions, invisible matter, buried structures, and enormous energetic environments concealed beneath the stars we can actually see. And understanding why parts of our galaxy are hotter than others requires understanding that hidden architecture first. Because the Milky Way is not merely a collection of stars scattered randomly through space. It is a structured organism of sorts, a rotating gravitational system with neighborhoods, crowded regions, quiet outskirts, invisible halos, turbulent interiors, and massive underlying frameworks shaping how matter and energy move over billions of years. In some ways, it behaves less like a static object and more like a weather system stretched across 100,000 light years, a very slow weather system, admittedly. Nobody has ever watched a spiral arm dramatically form during lunch. Still, the galaxy is constantly changing. Now, the first challenge humans faced when trying to understand the Milky Way was slightly awkward. We live inside it. That makes observing the galaxy rather difficult. It is a bit like trying to determine the shape of a forest, while standing in the middle of it surrounded by trees. For thousands of years, humans did not even realize the Milky Way was made of stars. It appeared as a blurry glowing streak because the human eye cannot individually resolve the enormous numbers of distant stars packed together there. Then, in the early 1600s, Galileo Galilei pointed a telescope toward the Milky Way and discovered something extraordinary. The haze dissolved into countless stars. Suddenly the galaxy became enormous, not a cloud, not mist, an immense stellar system. That realization fundamentally changed humanity's understanding of the universe. But even then, nobody knew the Milky Way's true shape. For a long time, astronomers imagined it as a relatively small, flattened system with the sun somewhere near the center. That assumption survived partly because interstellar dust blocks visible light extremely effectively. Space is not completely empty. Between stars drift huge clouds of dust and gas capable of obscuring distant regions. In visible wavelengths, those dusty regions appear like dark cracks running through the Milky Way. The problem is that dust hides enormous portions of the galaxy from ordinary telescopes. Imagine trying to map an entire city while thick fog permanently obscures half the streets. You would miss huge structures without even realizing they existed. That is exactly what happened with the Milky Way. Then astronomy expanded beyond visible light. Infrared telescopes began peering through dust clouds. Radio observations mapped hydrogen gas spread across enormous distances. Suddenly, astronomers could see the hidden skeleton of the galaxy itself, and the picture became far more complicated. The Milky Way, it turns out, is a barred spiral galaxy. Picture a giant rotating disk roughly 100,000 light-years across containing hundreds of billions of stars. Spiral arms curve outward from a dense central region like glowing rivers winding through darkness. But unlike the neat, clean spirals often shown in illustrations, the real Milky Way is messy. The spiral arms are uneven, gas clouds drift unpredictably, star formation erupts in clusters, magnetic fields twist invisibly through space, massive structures extend above and below the galactic plane, and surrounding everything lies an enormous halo almost completely invisible to human eyes. Our solar system sits about halfway out from the galactic center, inside a smaller structure called the Orion Arm, sometimes referred to as the Orion Spur. Compared to the crowded inner galaxy, our region is relatively quiet, which is probably fortunate. Life on Earth benefits enormously from living in a calmer galactic neighborhood. Closer to the center, stars are packed much more densely together. Supernova explosions occur more frequently. Radiation levels rise dramatically. Gravitational interactions become chaotic. The galactic center is not an especially relaxing place. It is beautiful, certainly, but calm, not particularly. At the heart of the Milky Way lies the central bulge, a swollen region filled with older stars densely packed together around Sagittarius A star, the supermassive black hole anchoring the galaxy gravitationally, this central region contains enormous amounts of gas, dust, radiation, and energetic activity. Temperatures there can become extreme compared to the quieter outer disk where we live. And importantly for our mystery, much of the galaxy's unusual heating appears connected directly or indirectly to this inner environment. But the structure of the Milky Way extends beyond the visible disk itself, far beyond. Surrounding the galaxy is something called the Galactic Halo, a huge, roughly spherical region containing sparse stars, globular clusters, hot gas, and one particularly important ingredient: dark matter. Now, dark matter is one of those topics capable of making conversations become extremely serious very quickly. Astronomers discovered long ago that galaxies rotate too fast for visible matter alone to hold them together gravitationally. Something invisible appears to provide additional mass. That invisible component is what scientists call dark matter. Nobody knows exactly what it is, which naturally makes physicists intensely enthusiastic. Dark matter does not emit light, absorb light, or interact normally with ordinary matter, yet its gravity shapes entire galaxies. In fact, the Milky Way is embedded inside an enormous dark matter halo extending far beyond the visible stars. Without it, the galaxy would likely fly apart. There is something slightly unsettling about realizing most of our galaxy's mass may consist of invisible material humans still cannot directly detect, rather like discovering your house is secretly supported by architectural ghosts. Still, dark matter's gravity profoundly influences the Milky Way structure, and possibly its temperature distribution as well. Gas moves through the galaxy under gravitational forces shaped partly by this invisible halo. Galactic collisions, mergers and flows evolve within that framework over billions of years. And because heat follows energy movement, understanding the galaxy's architecture becomes essential to understanding why certain regions become hotter. Now, the Milky Way does not rotate like a solid object. This part surprises many people. The inner regions orbit faster than the outer regions, creating something called differential rotation. Stars closer to the centre complete orbits more quickly than stars farther away. Our solar system takes roughly 230 million years to complete one orbit around the galactic centre, which means the last time Earth occupied this exact position in the galaxy, dinosaurs had not yet evolved. Galactic motion operates on wonderfully unreasonable timescales. Differential rotation also affects spiral arms themselves. Contrary to what many illustrations suggest, spiral arms are not rigid structures made from permanently fixed stars. Instead, they behave more like traffic jams in space. Stars and gas move into and out of spiral arms over time. The arms represent regions of higher density where gas compresses more strongly, triggering star formation, and where stars form, heat often follows. Massive young stars burn intensely hot and live fast, violent lives. Their ultraviolet radiation heats surrounding gas clouds. Their stellar winds stir turbulence into the interstellar medium. Their deaths as supernovae inject tremendous energy into surrounding space. Spiral arms therefore become active thermal environments, but not evenly. Certain arms contain richer star-forming regions than others. Some parts of the galaxy experience bursts of activity while neighbouring regions remain comparatively quiet. This uneven distribution of star formation contributes significantly to the Milky Way's thermal imbalance. And then there are the magnetic fields, invisible, enormous, and surprisingly important. The Milky Way contains galaxy-wide magnetic fields threading through gas clouds, spiral arms, and the halo itself. These fields influence how charged particles move through space, especially cosmic rays, high-energy particles accelerated by supernovae and other energetic events. Now, cosmic rays deserve a moment of appreciation because they sound fictional and yet are completely real. They are particles moving through the galaxy at nearly the speed of light, carrying enormous energies across vast distances. Some originate from supernova shockwaves. Others may come from black holes or extreme astrophysical environments, and magnetic fields guide their motion. Instead of travelling neatly in straight lines, cosmic rays spiral and scatter through the galaxy under magnetic influence, depositing energy into surrounding gas along the way. That energy contributes to heating, so already we can begin seeing why galactic temperature becomes complicated. Heat is not simply generated locally and left alone. Energy moves, particles travel, magnetic fields redirect flows, shockwaves propagate through interstellar gas, gravity reshapes structures over millions of years. The Milky Way behaves more like an interconnected ecosystem than a static arrangement of stars. Nowhere is this more obvious than near the galactic centre itself. As astronomers studied the inner Milky Way using radio, infrared, and X-ray telescopes, they discovered enormous hidden structures impossible to see in visible light alone. Huge molecular clouds, magnetic filaments stretching hundreds of light years, expanding shells of hot gas, and eventually the giant structures now known as the Fermi bubbles. These bubbles extend roughly 25,000 light-years above and below the galactic plane. They emit gamma rays, indicating extremely energetic particles and processes. To grasp their scale properly, consider this. The bubbles are each about 1/4 the diameter of the entire visible Milky Way. Enormous, and they appear linked directly to the galactic centre. Something happened there. Something energetic enough to inflate giant structures into the galactic halo itself. Perhaps Sagittarius A star underwent an active feeding phase long ago, ejecting huge jets of energy into surrounding space. Perhaps intense star formation triggered massive galactic winds powered by countless supernova explosions. Maybe both mechanisms contributed together. Whatever the cause, those structures altered the thermal landscape of the Milky Way significantly. Regions near them became hotter and more energetic, and importantly, not perfectly symmetrically. Astronomers have observed asymmetries in gas temperature, density, and energetic activity throughout portions of the galactic halo and inner disk. The Milky Way is not balanced like a perfectly designed machine. It is lopsided in places, disturbed, still carrying scars from ancient events. In fact, scientists now know the Milky Way has spent billions of years interacting with smaller galaxies orbiting nearby. Some were gradually absorbed entirely. Right now, the Milky Way is actively consuming smaller dwarf galaxies through gravity. Streams of stars torn from those galaxies stretch across space like tidal debris. Galactic cannibalism sounds dramatic because it is dramatic. And those mergers influence thermal structure too. Collisions compress gas, trigger star formation, disturb magnetic fields, and redistribute matter across enormous scales. Ancient merger events may still affect the present-day distribution of hot gas within the Milky Way halo. Even the halo itself appears surprisingly active. For a long time, astronomers imagined galactic halos as relatively empty regions surrounding visible galaxies. Instead, observations revealed enormous reservoirs of superheated gas extending far beyond the stellar disk. The Milky Way is wrapped in a diffuse halo of hot plasma reaching temperatures around 1,000,000 degrees. Again, this does not mean it feels like standing inside a furnace. The gas is extraordinarily thin. Still, energetically speaking, the halo contains tremendous amounts of heat, and intriguingly, that halo does not appear perfectly uniform either. Some regions seem denser or hotter than others. Astronomers suspect outflows from the galactic centre may continually feed energy into surrounding halo gas, creating giant circulation patterns operating over millions of years. The galaxy breathes, in a sense. Matter flows inward through spiral arms and gas clouds. Energy erupts outward through supernovae and black hole activity. Nothing remains static for very long, and hidden beneath the visible stars lies this vast dynamic infrastructure shaping where heat accumulates and where calmer regions survive. One reason humans underestimate the Milky Way's complexity is that the night sky appears two-dimensional. Stars seem scattered on a flat dome overhead, but the galaxy possesses extraordinary depth. Some stars visible tonight may lie only a few dozen light-years away. Others shine from thousands of light-years distant. Entire hidden structures sit buried behind dust clouds invisible to ordinary eyes. And much of the galaxy's most energetic activity occurs in wavelengths humans cannot naturally perceive. X-rays, gamma rays, radio emissions, infrared glow. The visible Milky Way is merely the skin of a far larger invisible system, rather like seeing only the lights of a city while remaining unaware of the tunnels, electrical grids, traffic systems, and underground machinery operating beneath it. Astronomy over the last century has essentially been humanity learning to see those hidden layers, and every new layer reveals additional complexity. The hotter half of the Milky Way is not simply hotter because one side accidentally wandered too close to a cosmic radiator. It is hotter because the galaxy possesses internal structure directing energy unevenly across space. Dense star-forming regions cluster in particular environments. Magnetic fields guide energetic particles asymmetrically. Ancient eruptions from the galactic center reshape surrounding gas. Supernova explosions inject heat into nearby regions. Hot plasma rises into the halo through giant outflows. And beneath everything, gravity governs the slow motion of matter through invisible frameworks extending far beyond the stars themselves. The Milky Way is less like a static spiral and more like a vast layered engine operating continuously over billions of years. A slow engine, a beautiful one, but an engine nonetheless. Some places in the universe are naturally quiet. Cold clouds drift slowly through darkness. Ancient stars burn steadily for billions of years. Entire regions of interstellar space remain so calm and empty that almost nothing changes there for immense stretches of time. The center of the Milky Way is not one of those places. In fact, if our solar system had formed near the galactic center, instead of out here in the relatively peaceful suburbs, life on Earth might never have developed at all. The environment there is simply too energetic, too crowded, too unstable. And that may be one of the biggest clues in our entire mystery, because once astronomers began studying the galactic center properly, they realized they were looking at a region capable of heating huge portions of the galaxy almost by itself. The first thing to understand is scale. When we say the center of the Milky Way, we are not talking about a single object or neat glowing dot. We are talking about an enormous region thousands of light years across, packed with stars, gas, dust, magnetic fields, radiation, and violent astrophysical activity layered together into one extraordinarily complicated environment. From Earth, the galactic center lies hidden in the direction of the constellation Sagittarius. Unfortunately for astronomers, huge clouds of dust sit between us and it, blocking visible light almost completely. If humans could see radio waves naturally, the night sky would look entirely different. The center of the galaxy would blaze. Immense structures would become visible, magnetic filaments would stretch through space, hot gas clouds would glow brightly, and the Milky Way would appear far more active and turbulent than the calm starry band our eyes perceive. Infrared telescopes eventually pierced much of the obscuring dust, and what they found was astonishing. Stars crowded together in extraordinary numbers, dense molecular clouds swirling chaotically, violent stellar winds colliding through space, and deep in the middle of it all, Sagittarius A star, the supermassive black hole anchoring the galaxy itself. Now, black holes often receive dramatic treatment in popular science, as though they spend every waking moment aggressively swallowing nearby objects like cosmic vacuum cleaners with emotional issues. The reality is slightly calmer, at least sometimes. Sagittarius A star is relatively quiet compared to the actively feeding black holes found in some galaxies. Right now, it consumes matter slowly. In astronomical terms, it is considered fairly dormant, but even dormant supermassive black holes are not exactly harmless decorations. Sagittarius A star contains roughly 4 million times the mass of the Sun, compressed into a surprisingly compact region. Its gravity dominates the central Milky Way. Entire stars orbit around it at incredible speeds. In fact, astronomers have directly tracked stars whipping around the invisible black hole over periods of years. Some move so quickly near closest approach that they reach several percent of the speed of light. Imagine an entire star system racing through space at millions of kilometers per hour, simply because the gravitational environment near the galactic center is so extreme. And yet, remarkably, Sagittarius A star itself is tiny compared to the vast region surrounding it. The galactic center behaves like a furnace, not merely because of the black hole, but because everything there becomes compressed together. More stars, more gas, more explosions, more radiation, more energy. Density changes everything. Near our solar system, stars are comfortably spaced. If the Sun vanished tomorrow, the nearest star would still sit over 4 light-years away. In the galactic center, stars crowd together thousands of times more densely. The night sky there would be overwhelming, bright stars everywhere, radiation flooding space continuously, supernova explosions occurring relatively frequently on cosmic timescales, massive young stars pouring ultraviolet radiation into surrounding gas clouds. The environment is energetic almost by default, and wherever enormous energy accumulates, heat follows. One major contributor to that heat is star formation itself. The galactic center contains giant molecular clouds dense enough to produce huge clusters of massive stars. These stars burn fast and hot, often living only a few million years before exploding as supernovae. Compared to the Sun's gentle, steady lifespan of roughly 10 billion years, massive stars behave rather recklessly. They consume fuel at astonishing rates. Their radiation ionizes surrounding gas. Their stellar winds blast material outward at tremendous speeds, and when they die, they release colossal amounts of energy into surrounding space. A single supernova can briefly outshine entire galaxies. Now imagine many occurring across the inner Milky Way over millions of years. The cumulative effect becomes enormous. Shockwaves heat nearby gas. Cosmic rays accelerate through magnetic fields. Hot plasma expands outward into surrounding regions. And gradually the galactic center develops into an environment fundamentally hotter and more turbulent than quieter outer regions. Astronomers studying the central molecular zone, a dense region surrounding Sagittarius A star, discovered temperatures there are unexpectedly high. Gas clouds that should have cooled more efficiently remain strangely warm. Some molecular gas reaches temperatures hundreds of degrees above what ordinary starlight alone should produce. Which immediately raises another question. What exactly is heating it? That mystery remains partially unresolved even today. Several mechanisms likely contribute simultaneously. Turbulence generated by colliding gas clouds may dissipate energy as heat. Cosmic rays streaming through the region may warm molecular gas. Magnetic fields twisting and reconnecting could release enormous stored energy. Supernova remnants inject heat continuously, and then there is the black hole itself. Although Sagittarius A star appears relatively calm now, evidence suggests it may have been far more active in the past. This realization changed how astronomers viewed the Milky Way entirely. For many years, scientists assumed our galaxy possessed a fairly ordinary, quiet central black hole, compared to the violent active galactic nuclei observed elsewhere in the universe. Then observations began revealing strange clues. X-ray echoes appeared in surrounding gas clouds, suggesting bursts of radiation had occurred in the past. Giant outflows extended above and below the galactic plane. The Fermi bubbles hinted at enormous energetic eruptions. Suddenly, Sagittarius A star no longer looked entirely dormant. Instead, it began resembling a sleeping volcano, that may have experienced dramatic eruptions not terribly long ago in cosmic terms. If Sagittarius A star consumed large amounts of matter several million years ago, the resulting energy release could have heated huge regions of the inner galaxy. Black holes themselves do not emit light directly, but matter falling toward them becomes compressed and accelerated tremendously, heating into glowing disks of plasma capable of radiating enormous energy. In actively feeding galaxies, these accretion disks can outshine all surrounding stars combined. Jets of particles shoot outward near light speed. Radiation floods interstellar space. Entire galactic environments become reshaped. The Milky Way does not currently display that level of activity, but evidence suggests smaller-scale eruptions likely occurred in the past, enough to leave scars still visible today. And those scars appear hot. One especially fascinating discovery involves giant magnetic filaments stretching through the galactic center. These structures extend for dozens or even hundreds of light years, glowing in radio wavelengths. They trace invisible magnetic fields threading through the inner galaxy. Nobody fully understands them yet, which is usually a sign astronomers become very interested. Magnetic fields in the galactic center are extraordinarily strong compared to many outer regions. Those fields trap and guide charged particles, influencing how energy moves through surrounding space. Cosmic rays spiral along magnetic lines. Plasma becomes confined into giant structures. Magnetic reconnection events release bursts of energy somewhat similar to solar flares, except on much larger scales. All of this contributes to heating. The galactic center is not merely hot because it contains many stars. It is hot because countless energetic processes overlap there simultaneously. Gravity compresses matter inward. Stars form rapidly. Supernovae explode. Magnetic fields twist. Cosmic rays accelerate. Black hole activity stirs surrounding gas. The entire region behaves like an enormous interconnected engine, continuously converting gravitational energy into heat and radiation. And importantly, that energy does not stay neatly confined to the center. Some of it escapes outward. Astronomers have detected huge galactic winds flowing away from the central Milky Way. These winds carry hot gas, magnetic fields, and energetic particles thousands of light years into surrounding space. In effect, the galactic center breathes heat outward into the galaxy. Imagine a giant furnace venting energy continuously over millions of years. Gradually, surrounding regions become warmer, more turbulent, and more energized. This may explain why certain portions of the galactic halo appear hotter than expected. Energy from the central galaxy likely feeds into those outer regions through long-term outflows. And yet, intriguingly, the heating does not appear perfectly symmetrical. Some structures extend farther in particular directions. Some regions glow more brightly in X-rays or gamma rays than others, which suggests the galactic center itself may not operate evenly. Gas clouds there are distributed irregularly. Star formation occurs in bursts. Magnetic fields fluctuate chaotically. Black hole feeding episodes may happen unevenly depending on available material. In other words, the furnace burns unpredictably. Now, there is another reason the galactic center fascinates astronomers so deeply. It offers a nearby laboratory for understanding extreme galactic environments throughout the universe. Other galaxies contain active centers vastly more violent than ours. Some produce enormous jets visible across millions of light years. Others radiate so intensely their cores outshine surrounding stars completely. Compared to those monsters, the Milky Way center is relatively mild. But because it is nearby, scientists can study it in extraordinary detail. And the more detailed those observations become, the stranger the region appears. Take the temperatures of surrounding plasma, for instance. Some hot gas near the galactic center reaches millions of degrees. X-ray telescopes reveal diffuse glowing plasma permeating large regions of space. Again, This does not mean space there feels like standing inside a furnace in the ordinary human sense. The gas remains extremely thin. Still, energetically speaking, it is extraordinarily hot. And keeping such diffuse plasma heated over long timescales is difficult. Without continuous energy input, it should cool gradually through radiation. So the existence of persistent hot plasma suggests ongoing heating mechanisms remain active. Perhaps turbulence, perhaps magnetic interactions, perhaps cosmic rays, possibly lingering effects from past black hole eruptions, most likely several processes together. Astronomers increasingly suspect that the galactic center operates through feedback cycles. Stars form from collapsing gas clouds. Massive stars produce radiation and winds. Supernovae inject energy into surrounding gas. That energy stirs turbulence and drives outflows. Some gas escapes outward, while some eventually falls back inward. Meanwhile, Sagittarius A occasionally consumes material and releases additional energy. The entire environment self-regulates in complicated ways over millions of years. Feedback becomes heat. Heat becomes structure. Structure shapes future star formation. And slowly, the galaxy evolves. One particularly eerie realization emerged from recent studies. The Milky Way may have looked dramatically different only a few million years ago. That sounds like an enormous timescale from a human perspective, and to be fair, it absolutely is. But cosmically speaking, a few million years is remarkably recent. At the time, some suspected eruptions occurred near Sagittarius, a star. Early human ancestors were already walking across Earth. Which means that while primitive humans learned to use stone tools beneath African skies, gigantic outflows may have been erupting from the centre of our galaxy. There is something wonderfully unsettling about that. Human history unfolds on such tiny scales compared to galactic evolution, and yet the two overlap. Ancient hominins looked upward while invisible gamma-ray bubbles expanded tens of thousands of light-years overhead. Of course, nobody noticed. The structures remained hidden from human eyes until modern telescopes uncovered them. But they were there all along, and perhaps they still shape the temperature distribution of the Milky Way today. The farther astronomers probe into the galactic center, the clearer one thing becomes. This region is not passive. It is active, restless, continuously injecting energy into surrounding space through overlapping astrophysical processes. And because the center influences enormous portions of the galaxy gravitationally and energetically, understanding its behavior may explain why some regions of the Milky Way remain dramatically hotter than others. At first glance, the Milky Way seems like it should behave symmetrically. A spiral galaxy rotating through space ought to distribute its stars, gas and energy somewhat evenly over large scales. Not perfectly, of course. Nature rarely bothers with perfect balance. But broadly speaking, astronomers once expected the galaxy to act like a relatively stable rotating system, where conditions averaged out over time. Then the observations started arriving. Not all at once. Little clues appeared first. Certain regions emitted stronger X-rays than expected. Gamma-ray observations revealed uneven concentrations of high-energy radiation. Surveys of hot gas showed asymmetrical temperature distributions extending above and below the galactic plane. Some areas of the halo appeared denser and more energetic than neighbouring regions. And slowly, a strange realization emerged. Parts of the Milky Way were behaving more violently than others. Not merely busier, hotter, more turbulent, more energetic. Almost as though the galaxy itself had a preferred direction for releasing energy. Naturally, astronomers wanted to know why. One important thing to understand is that galaxies are shaped by history as much as physics. The Milky Way we see today is not some pristine object that formed neatly and remained unchanged ever since. It is the accumulated result of billions of years of collisions, eruptions, star formation, gravitational disruptions and flowing matter. Every region carries traces of past events, and some regions carry far more scars than others. The strongest clue pointing toward this imbalance came from high-energy observations of the inner galaxy. In visible light, the Milky Way still looks relatively calm. But once astronomers examined it in gamma rays and X-rays, enormous asymmetrical structures began appearing. Some regions glowed intensely, others remained comparatively quiet. The pattern was impossible to ignore. Particularly striking were the gigantic outflows extending above and below the galactic centre. These structures suggested that tremendous amounts of energy had escaped from the inner Milky Way at some point in the past. But here is where things become especially interesting. The energy did not spread evenly. If you drop a stone into calm water, ripples expand outward symmetrically, but the Milky Way's energetic structures resemble water disturbed by repeated uneven impacts from different directions over millions of years. The galaxy looks stirred, disturbed, like something repeatedly punched heat into one side harder than the other. One possible explanation involves the distribution of star formation itself. The Milky Way does not create stars evenly across all regions. Spiral arms contain dense molecular clouds where stars form actively, while other areas remain relatively quiet. Massive stars, in particular, contribute enormous amounts of energy into surrounding space through radiation, stellar winds, and eventually supernova explosions. And those massive stars are not spread uniformly throughout the galaxy. Some regions contain clusters of extremely energetic star-forming activity, known as starburst regions. There, giant stars form in large numbers over relatively short periods. These stars live fast and die violently. A massive star may burn through its fuel in only a few million years before exploding as a supernova. During that brief lifespan, it floods surrounding space with ultraviolet radiation and powerful stellar winds. Then comes the explosion. A supernova releases staggering amounts of energy almost instantly. Shockwaves blast through nearby gas clouds at tremendous speeds, compressing, heating, and stirring surrounding material. One supernova alone can reshape entire local environments. Now imagine thousands occurring across the inner galaxy over millions of years. Gradually some regions become saturated with heat and turbulence, while others remain calmer. Astronomers suspect this uneven stellar activity contributes heavily to why one side of the Milky Way appears more energetic than the rest. But stellar explosions alone probably do not explain the full scale of the observed asymmetry. The structures are simply too large. That realization pushed scientists toward another possibility. The galactic center itself may have erupted asymmetrically. Now black holes do not always feed continuously. Supermassive black holes often alternate between quiet periods and active phases depending on how much matter falls inward. Sagittarius A appears relatively calm today, but evidence increasingly suggests it experienced energetic feeding episodes in the past. When matter spirals toward a black hole, enormous friction and compression heat the material intensely. Before crossing the event horizon, gas can radiate tremendous energy outward. If enough matter falls inward quickly, the resulting outburst can affect entire galactic environments. Jets may erupt. Radiation may flood surrounding space. Hot plasma may expand outward through the galaxy. And importantly, these eruptions do not necessarily occur symmetrically. Gas clouds near the galactic center are chaotic and unevenly distributed. If Sagittarius A consumed material from one preferred direction more strongly than another, the resulting energy release could have shaped nearby regions unevenly. Some astronomers suspect exactly this happened. Perhaps several million years ago, Sagittarius A entered a more active state and blasted energy outward into surrounding space. That event may have heated enormous structures extending preferentially through certain regions of the Milky Way. The evidence supporting this idea became dramatically stronger after the discovery of the Fermi bubbles. These gigantic structures tower above and below the galactic plane, glowing in gamma rays. They extend roughly 25,000 light-years in each direction from the center. They are enormous beyond ordinary comprehension, If visible to human eyes, they would dominate huge sections of the sky. And crucially, they appear linked directly to past energetic activity in the galactic centre. The bubbles themselves are not perfectly uniform. Their edges, internal structures, and surrounding environments display asymmetries suggesting complicated formation histories. Something violent happened there, possibly multiple times, and whatever happened likely redistributed heat across huge portions of the galaxy. Now, there is another layer to this mystery involving something invisible but extremely important. Cosmic rays. Cosmic rays are high-energy particles moving through space at extraordinary speeds, often close to the speed of light. Many originate from supernova explosions or energetic black hole environments, and they carry enormous amounts of energy across the galaxy. When cosmic rays collide with gas clouds or interact with magnetic fields, they deposit energy into surrounding matter. This contributes to heating and radiation production. The Milky Way is flooded with cosmic rays continuously, but again, not evenly. The distribution of cosmic rays depends heavily on where they originate and how magnetic fields guide their motion. And the galaxy's magnetic fields are astonishingly complicated. Invisible magnetic structures thread through the Milky Way on enormous scales. Charged particles spiral along those fields instead of moving neatly in straight lines. Think of cosmic rays less like bullets, and more like tiny energetic dancers forced to follow invisible twisting highways through space. Some regions trap particles more efficiently than others. Some channel energy outward into the halo. Some allow particles to escape more freely. This means heat generated by cosmic rays can accumulate unevenly across different galactic environments. In fact, observations suggest that magnetic structures near the galactic centre may funnel energetic particles preferentially into certain directions, helping explain why some regions glow more intensely in gamma rays and X-rays. The Milky Way is not merely hotter in places because more energy exists there. It is hotter because energy moves differently through different structures, and those structures are deeply asymmetrical. Another fascinating clue involves the galactic halo itself. For a long time, astronomers imagined the halo surrounding the Milky Way as relatively smooth and quiet. Instead, modern observations revealed giant reservoirs of hot plasma extending far beyond the visible disk, and once scientists mapped portions of that halo carefully, they noticed irregularities. Some regions appeared denser, some hotter, some more enriched with heavy elements produced by stars. This suggests that material from the inner galaxy has been flowing outward unevenly over long periods of time. Galactic winds likely play a major role here. Near the galactic centre, overlapping supernova explosions and energetic stellar winds can combine into enormous outflows, carrying gas upward away from the disk. These winds transport heat, magnetic fields, cosmic rays, and chemically enriched material into the halo. But those outflows are shaped by local conditions. Dense gas clouds block some directions. Magnetic fields redirect flows. Past eruptions carve channels through surrounding material. As a result, galactic winds become uneven. Some regions receive far more energetic input than others. Over millions of years, this creates large-scale thermal asymmetries across the Milky Way. And intriguingly, there may be another contributing factor. The galaxy itself is moving. The Milky Way travels through intergalactic space surrounded by diffuse gas and embedded within the local group of galaxies. Interactions between the galactic halo and surrounding environments may influence how hot gas accumulates around different regions. Some astronomers compare it loosely to airflow around a moving object. As the galaxy moves, surrounding material may compress or interact differently on various sides of the halo. This effect alone likely does not explain the full asymmetry, but combined with internal energetic processes, it may contribute additional imbalance. Then there are galactic mergers. The Milky Way has spent billions of years absorbing smaller galaxies. Right now, remnants of ancient mergers still stretch across space as stellar streams and disrupted structures. These collisions disturb gas distributions dramatically. Imagine pouring cream into coffee and stirring unevenly. The resulting swirls persist for a while before smoothing out. Galactic mergers operate similarly, except instead of cream and coffee, the ingredients are stars, gas clouds, dark matter, magnetic fields, and enormous reservoirs of hot plasma interacting over millions of years. Past mergers may have tilted or disturbed portions of the Milky Way's halo, creating long-lasting asymmetries in how heat spreads through surrounding regions. In other words, the hotter half of the galaxy may partly reflect ancient collisions whose original galaxies no longer even exist as separate objects. The Milky Way remembers its history thermally. Heat becomes archaeology. Now, one especially strange feature astronomers observed involves something called the North Polar Spur. This gigantic structure extends high above the galactic plane and glows strongly in radio waves and X-rays. It may represent part of a huge ancient shockwave or outflow linked to energetic events near the galactic center. Its origin remains debated. Some scientists suspect nearby supernova activity contributed to it. Others think it may connect directly to ancient eruptions from Sagittarius A star. Either way, it highlights the same recurring theme. The galaxy contains enormous asymmetrical energetic structures extending across vast distances, and those structures continue influencing surrounding temperatures today. One of the more comforting aspects of all this, oddly enough, is how invisible most of it remains from Earth. Our night sky still appears peaceful. The stars overhead do not look violent. The Milky Way still stretches quietly across darkness like a calm river of light. Human eyes evolved to perceive visible wavelengths useful for survival, not gamma rays from galactic plasma bubbles, thankfully. Because if we could naturally see the high-energy universe, the night sky would appear much more chaotic. Radiation storms, hot gas clouds, magnetic structures, energetic shockwaves. The galaxy would look alive in an entirely different way, and perhaps a little alarming before bedtime. Still, hidden or not, those energetic structures shape the Milky Way continuously. They influence star formation, they redistribute gas, they heat surrounding plasma, they sculpt the halo itself. The galaxy behaves less like a balanced static wheel, and more like an evolving ecosystem full of uneven flows and lingering scars from ancient violence. And the farther astronomers investigate, the more it seems likely that no single explanation accounts for the hotter half of the Milky Way. Instead, multiple processes overlap: supernova explosions, starburst activity, magnetic turbulence, cosmic rays, galactic winds, ancient black hole eruptions, past mergers, halo interactions. Together, they create a galaxy where energy accumulates unevenly across space. Some regions cool quietly, others remain restless for millions of years, and perhaps the most remarkable part is that humans discovered all this only recently. For most of history, nobody suspected enormous hidden asymmetries stretched across our galaxy at all. Ancient civilizations looked upward and saw beauty. Modern telescopes looked deeper and found turbulence beneath that beauty. A giant stellar system still carrying traces of ancient eruptions and invisible heat, moving through darkness, which naturally raises another question. If these violent structures exist, what exactly caused them in the first place? Long before humans existed, before Earth had cities or telescopes or anyone capable of looking upward and asking difficult questions about gamma rays before bedtime, something enormous may have happened near the centre of the Milky Way. Not enormous by human standards, enormous by galactic standards. An event powerful enough to blast energy tens of thousands of light years into surrounding space. Powerful enough to heat giant reservoirs of gas. Powerful enough to leave scars still visible today in X-rays and gamma rays millions of years later. And perhaps most fascinating of all, astronomers only discovered evidence for this event recently. For almost all of human history, the clues were hidden in wavelengths invisible to our eyes. The stars overhead looked calm. Meanwhile, gigantic structures quietly loomed above and below the galaxy itself. The first major hint arrived through observations from NASA's Fermi Gamma-ray Space Telescope, launched in 2008 to study the high-energy universe. Gamma rays represent some of the most energetic forms of light in the existence. They are produced in extreme environments, supernova explosions, black hole jets, neutron stars, particle collisions, and violent cosmic events capable of accelerating matter to incredible energies. Ordinary stars like the Sun emit relatively little gamma radiation, so when astronomers detect large gamma-ray structures, they immediately know something energetic is happening, or happened. In 2010, scientists analysing data from the Fermi telescope noticed something strange extending above and below the centre of the Milky Way. Actually as strange, maybe putting it mildly. They discovered two gigantic balloon-like structures stretching roughly 25,000 light-years in opposite directions from the galactic centre. The structures glowed brightly in gamma rays. They possessed surprisingly sharp edges, and they were absolutely enormous. These became known as the Fermi bubbles. Now, one of the most unsettling things about the Fermi bubbles is how close we came to not noticing them at all. They had likely existed the entire time humans evolved as a species. Ancient people lived, travelled, built civilizations, watched stars, invented calendars, crossed oceans, wrote poetry, and argued about taxes beneath a sky containing giant invisible galactic structures larger than many entire galaxies. The universe often hides its most dramatic features in wavelengths humans cannot naturally see. And once astronomers identified the bubbles, the immediate question became obvious. What created them? Because structures that large require extraordinary amounts of energy. Scientists began estimating how much power would be needed to inflate gigantic gamma-ray emitting bubbles extending so far above and below the Milky Way. The answer was alarming. Something released energy equivalent to millions of supernova explosions. Possibly more. Suddenly, the Milky Way no longer seemed like a relatively quiet spiral galaxy with a sleepy central black hole. It started looking like a galaxy with a history, a violent history, and the evidence was still hanging overhead in enormous glowing lobes. Now, there are currently two leading explanations for the origin of the Fermi bubbles. Both are dramatic. The first possibility involves Sagittarius A star, the supermassive black hole at the centre of the galaxy. Although relatively calm today, Sagittarius A star may once have entered a much more active phase. If large amounts of gas fell inward rapidly, the black hole could have released tremendous energy through radiation and particle outflows. In actively feeding galaxies, black holes often generate enormous jets shooting outward perpendicular to the galactic disk. Those jets can travel huge distances while heating surrounding gas and accelerating particles to extraordinary energies. Some astronomers suspect the Fermi bubbles may be remnants of such an event. Perhaps several million years ago, Sagittarius A star briefly awakened. Not permanently, just long enough to erupt. Matter spiraled inward, plasma heated intensely, radiation flooded outward, and giant outflows blasted into the halo surrounding the Milky Way. Over time, those outflows expanded into the structures astronomers now observe. If true, it means the Milky Way's centre may once have resembled a miniature active galactic nucleus, a far more energetic version of the relatively calm environment we see today, and importantly for our larger mystery, such an eruption would have heated enormous portions of surrounding space unevenly. The second major possibility involves extreme star formation near the galactic centre. Remember, the inner Milky Way contains dense molecular clouds capable of producing huge clusters of massive stars. Massive stars live fast and die violently as supernovae. Now imagine not one supernova, not 10, but thousands occurring across relatively short cosmic timescales. Their combined shockwaves could merge into gigantic galactic winds, powerful enough to inflate the Fermi bubbles gradually over millions of years. This idea is known as the nuclear starburst hypothesis. Essentially, the galactic centre may have undergone an intense burst of star formation that flooded surrounding space with energy, and honestly, both explanations may be partly correct. Astronomy often disappoints people hoping for neat single answers. The universe prefers overlapping processes. Perhaps starburst fed additional material towards Sagittarius A star. Perhaps black hole activity and supernova-driven winds worked together. Perhaps multiple eruptions occurred over time instead of one single event. The galaxy rarely behaves in tidy ways convenient for textbooks. Still, whichever mechanism dominated, one conclusion became increasingly unavoidable. The Milky Way experienced a major energetic event in the relatively recent cosmic past, and traces of that event may still influence the galaxy today. One especially fascinating detail involves the shape of the bubbles themselves. They appear surprisingly symmetrical overall, extending both above and below the galactic plane. Yet internally, they contain complicated substructures, temperature variations, and asymmetries suggesting turbulent formation histories. Some regions glow more strongly, some appear hotter, some show evidence of shock fronts where expanding material collided with surrounding gas. The structures look alive in a sense, not static, still evolving, and because the bubbles contain extremely energetic particles, they continue emitting radiation even now. The explosion, whatever its origin, may be long over, but its echoes remain. There is something deeply eerie about that idea. An ancient galactic event occurring millions of years ago, still leaving visible traces across tens of thousands of light years. The Milky Way remembers its violence for a very long time. Now, the Fermi bubbles are not the only evidence supporting ancient eruptions. X-ray telescopes later discovered additional giant structures overlapping parts of the bubbles. These X-ray emissions suggest surrounding gas was heated tremendously, likely by powerful shockwaves moving through the galactic halo. And the temperatures involved are astonishing. Millions of degrees. Again, the gas remains extremely diffuse, so this is not heat in the ordinary human sense. Still, energetically speaking, it represents a vast amount of thermal energy distributed across enormous scales. Some scientists compare the expanding structures loosely to enormous explosions inside Earth's atmosphere. Imagine detonating something so powerful that shockwaves continue spreading for millions of years while heating surrounding gas over distances larger than entire galaxies. Actually, that analogy still understates the scale somewhat. Galactic events quickly become unreasonable when translated into human experience. What matters for our mystery is this. If the galactic centre erupted violently in the past, then much of the Milky Way's present temperature imbalance may represent lingering fallout from those events. The hotter half of the galaxy may not simply be naturally hotter. It may have been heated, disturbed, reshaped, and because interstellar space is so diffuse, heat dissipates slowly over galactic timescales. Shockwaves can travel for millions of years. Cosmic rays remain trapped by magnetic fields. Hot plasma drifts gradually through the halo. The galaxy carries thermal memory. Another intriguing clue comes from chemical enrichment. Supernova explosions produce heavy elements like iron, oxygen, silicon, and calcium. Those elements spread outward into surrounding gas after stars explode. Astronomers observing portions of the galactic halo found evidence of chemically enriched material, extending far from the centre. This strongly suggests that matter from the inner galaxy was blown outward into surrounding space. The Milky Way did not merely release energy, it exhaled matter itself, and where that matter travelled, heat often travelled with it. Some researchers suspect giant galactic fountains may operate continuously. Gas heated near the centre rises outward into the halo, cools gradually, then eventually falls back toward the disk again under gravity, a kind of enormous galactic circulation system operating over millions of years. the galaxy breathes, slowly, patiently, and perhaps unevenly, because these outflows are shaped by local conditions. Gas density varies, magnetic fields redirect plasma, previous eruptions carve channels through surrounding material, even slight asymmetries become amplified over enormous timescales and distances. As a result, some regions of the Milky Way may receive significantly more energetic input than others. One particularly interesting discovery involves giant microwave-emitting structures called the Galactic haze. This haze overlaps portions of the Fermi bubbles and may represent synchrotron radiation, emissions produced when high-energy electrons spiral around magnetic fields near light speed. In simpler terms, astronomers found additional evidence that enormous populations of energetic particles continue moving through those regions today. The galactic center appears to have launched a long-lasting storm of high-energy activity into surrounding space, and parts of that storm may still be ongoing. Now, naturally, scientists wanted to determine when all this happened. Estimating ages for structures tens of thousands of light-years across is not exactly straightforward. Astronomers use expansion speeds, radiation properties, cooling rates, and computer simulations to reconstruct possible timelines. Current estimates suggest the Fermi bubbles formed somewhere between a few million and perhaps 10 million years ago, which is astonishingly recent on galactic timescales. Remember, the Milky Way itself is over 13 billion years old. An eruption only a few million years ago is almost current events by comparison. At the time these structures may have formed, Earth already contained early human ancestors walking beneath African skies, which means our species evolved inside a galaxy still recovering from relatively recent energetic upheaval. There is something wonderfully humbling about that. Human history feels long to us. Civilizations rise and fall over thousands of years. Empires come and go. Languages appear and disappear. Meanwhile, the galaxy quietly carries scars from explosions older than humanity itself, yet recent enough to still glow overhead. And perhaps the strangest part is that Earth survived all this comfortably. Despite the enormous scales involved, we remain safely distant from the galactic center. The Milky Way is huge enough that even colossal eruptions dissipate enormously before reaching our region. If our solar system orbited much closer to the center, things might have been different. Radiation exposure could rise dramatically. Nearby supernovae would occur more frequently. High-energy particle fluxes might alter planetary atmospheres. Life could struggle in such unstable environments. Instead, Earth sits in a relatively calm neighborhood, far enough away to observe the fireworks safely from a distance. A fortunate arrangement, really. Because galaxies are not gentle places overall. They merely appear gentle from far away. And the farther astronomers investigate these ancient structures, the more they realize the Milky Way may still be shaped by them today. Hot gas continues drifting through the halo. Magnetic fields still guide energetic particles. Cosmic rays still carry traces of ancient acceleration events. Some portions of the galaxy remain hotter precisely because they were once blasted by extraordinary eruptions. The effects linger. Millions of years later, they linger. In a sense, the galaxy is still cooling down, still redistributing energy from events long finished, still glowing unevenly because ancient violence disturbed its balance. When most people picture space, they imagine emptiness, a vacuum, stillness, dark silence interrupted occasionally by stars. And to be fair, space is mostly empty. The distances between objects in the universe are so enormous that even galaxies themselves are largely made of nothing at all. If the sun were shrunk to the size of a tennis ball, the nearest star would still sit hundreds of kilometers away. But emptiness in astronomy can be misleading, because even the thin material drifting between stars matters enormously when stretched across galactic scales. And once astronomers began studying the Milky Way carefully beyond visible light, they discovered that our galaxy is threaded by invisible structures shaping how energy moves through space itself. Magnetic fields, cosmic rays, hot plasma flowing through enormous channels, invisible currents extending thousands of light years. Suddenly, the Milky Way started looking less like a collection of isolated stars and more like a giant interconnected electrical system. Actually, electrical system might still undersell things slightly. The galaxy behaves in some ways like an ocean made of charged particles, a very thin ocean, a very hot ocean, but one constantly stirred by gravity, explosions and magnetism, and these hidden flows may explain a great deal about why certain regions of the Milky Way remain far hotter and more violent than others. Now, magnetic fields are strange things, even here on Earth. You cannot see them directly, yet they shape reality constantly. A compass needle responds to Earth's magnetic field invisibly. Solar storms interact with Earth's magnetosphere to create auroras. Electricity and magnetism intertwine fundamentally at deep levels of physics. In space, magnetic fields become even more important, because so much matter exists as plasma. Plasma, you may remember, is gas heated so intensely that electrons break free from atoms. The result is a soup of charged particles highly sensitive to magnetic forces, and the Milky Way contains enormous amounts of plasma. Hot plasma fills portions of the galactic halo. Supernova remnants contain expanding plasma shockwaves. Stellar winds carry plasma outward from stars continuously. Even the thin gas between stars often exists in partially ionized form. Wherever plasma moves, magnetic fields follow. And wherever magnetic fields twist or reconnect, energy gets released. The galaxy is full of this activity. The problem is that humans cannot naturally see magnetic fields. They remained hidden for most of history until astronomers developed ways to detect their effects indirectly. One important clue came through radio observations. Charged particles moving through magnetic fields emit a type of radiation called synchrotron radiation. This glow appears strongly in radio wavelengths and allows astronomers to trace otherwise invisible magnetic structures. And once scientists began mapping those structures in the Milky Way, the results were astonishing. Huge magnetic filaments stretched across the galactic center. Giant loops rose above the disk. Invisible field lines threaded spiral arms and halo regions across tens of thousands of light years. The galaxy was magnetized on enormous scales, not weakly either. The inner Milky Way contains magnetic fields far stronger and more chaotic than many outer regions, and those fields influence how heat moves through the galaxy, because heat in space often travels not simply through ordinary gas motion, but through energetic charged particles called cosmic rays. Now, cosmic rays sound fictional enough that people occasionally assume scientists named them after a comic book, but they are entirely real, and surprisingly intense. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, moving through space at tremendous speeds. Some travel at over 99% the speed of light. Where do they come from? Many originate from supernova explosions. When massive stars explode, expanding shockwaves accelerate surrounding particles through powerful electromagnetic processes. Imagine giant stellar explosions functioning like natural particle accelerators scattered throughout the galaxy. Those particles then stream outward, carrying enormous amounts of energy. Other cosmic rays may originate near black holes, pulsars, or energetic plasma structures in the galactic center. The Milky Way is constantly flooded with them. Right now, cosmic rays are passing through your body harmlessly. Actually, they have been this entire time. The universe is wonderfully inconsiderate like that. Thankfully, Earth's atmosphere and magnetic field protect us from most dangerous effects. But in open space, cosmic rays become a major energetic component of galactic environments. And importantly, cosmic rays do not travel randomly. Magnetic fields guide them. Charged particles spiral around magnetic lines, rather than moving in neat, straight paths. This creates enormous invisible networks channeling energy across the galaxy. Some regions trap cosmic rays effectively, others allow them to escape. Some areas become saturated with energetic particles over millions of years, and wherever cosmic rays accumulate, surrounding gas tends to heat up. Gradually, astronomers realized the Milky Way's temperature distribution could not be understood properly without including these invisible energetic flows. The galaxy is not heated solely by stars shining locally. Energy moves, it travels through magnetic pathways, it accumulates unevenly. And nowhere is this more dramatic than near the galactic center. There, magnetic structures become incredibly tangled and powerful. Radio telescopes revealed long, thin filaments stretching vertically through the inner galaxy like giant invisible wires. Some extend for hundreds of light years. Scientists still debate exactly how these structures form, which is usually a sign the universe has become complicated again. One leading idea suggests turbulence near the galactic center twists magnetic fields into concentrated strands. Cosmic rays trapped inside those fields then emit synchrotron radiation visible in radio wavelengths. Essentially, the center of the Milky Way may contain enormous magnetized rivers of energetic particles flowing through space, and because those flows are uneven, heat becomes uneven too. Another important process involves magnetic reconnection. This occurs when magnetic field lines twist, break, and reconnect suddenly, releasing stored energy explosively. The Sun experiences magnetic reconnection regularly during solar flares. Huge amounts of energy erupt outward as magnetic structures rearrange themselves. Now imagine similar processes occurring across much larger galactic environments. The energy released can heat plasma dramatically and accelerate additional cosmic rays. Some astronomers suspect magnetic reconnection near the galactic center contributes significantly to heating surrounding gas. The galaxy may contain giant magnetic storms unfolding slowly over enormous scales, and because magnetic fields differ across regions, some parts of the Milky Way become far more energetically active than others. One especially fascinating discovery came from observations of polarized radio emissions. Polarization allows astronomers to infer the orientation of magnetic fields in space. By studying polarized light from the Milky Way, scientists found evidence for large-scale magnetic structures extending into the galactic halo itself. The galaxy's magnetic system does not stop at the visible disk. It surrounds the Milky Way, threads through it, connects distant regions together, and likely helps transport energy outward from the galactic center into surrounding halo gas. This becomes extremely important for explaining why parts of the halo remain surprisingly hot. Without continuous heating, diffuse hot plasma should cool gradually over time. Yet observations show enormous regions of million-degree gas extending far around the Milky Way. Some mechanism must keep injecting energy. Cosmic rays and magnetic fields may provide part of that answer. Cosmic rays carry pressure as well as energy. Large populations of energetic particles can actually help drive galactic winds outward into the halo. Think of them almost like invisible gas contributing to enormous outflows rising from the galactic center. These outflows transport hot plasma, magnetic fields, and cosmic rays together, and once again, they do not spread perfectly symmetrically. Magnetic structures redirect them unevenly. Dense gas clouds block some paths. Previous eruptions carve channels favoring certain directions. The result is a galaxy where energetic flows become concentrated into particular regions. Some areas cool quietly. Others remain flooded with energetic particles for millions of years. Now, there is another reason plasma behaves differently from ordinary gas. Plasma responds collectively. Because charged particles interact electromagnetically over long distances, plasma can organize itself into filaments, waves, and enormous coherent structures. This gives galactic plasma environments a strangely fluid, almost atmospheric quality. Astronomers sometimes describe the interstellar medium as turbulent, and that word is important. The Milky Way is not still inside. Gas clouds collide, shockwaves expand, magnetic fields twist, plasma churns through enormous regions, cosmic rays diffuse outward unevenly. The galaxy possesses weather of a kind. Not weather made of rain and clouds, but weather made of magnetized plasma and high-energy particles. And like weather on Earth, some regions become stormier than others. One clue supporting this picture comes from observations of diffuse gamma-ray emissions across the Milky Way. Gamma rays often form when cosmic rays collide with interstellar gas. By mapping gamma-ray brightness, astronomers can estimate where cosmic rays concentrate most strongly. And once again, the inner galaxy stands out dramatically. The galactic center glows intensely in high-energy radiation. Some surrounding regions appear overloaded with energetic particles, others remain relatively calm. The imbalance suggests the Milky Way's central engine continuously injects energy into specific pathways shaped partly by magnetic structures. Even more intriguingly, some observations hint that cosmic rays may linger inside certain galactic regions much longer than expected. Magnetic turbulence can trap particles efficiently, causing energy to accumulate over time. Imagine invisible reservoirs of energetic particles slowly heating, surrounding plasma across millions of years. The galaxy may contain enormous hidden energy storage systems woven through magnetic fields. Now, one especially strange aspect of cosmic rays is how difficult they are to trace back to their origins. Because magnetic fields bend their paths constantly, cosmic rays arriving near Earth have usually wandered through the galaxy for immense periods. By the time one reaches us, its original direction is largely scrambled. In a sense, the Milky Way randomizes them. This makes reconstructing energetic galactic processes surprisingly difficult. Astronomers often detect the consequences of cosmic rays more easily than the particles themselves. Heating, radiation, shockwaves, synchrotron emissions. These become clues pointing toward hidden energetic flows, and increasingly those clues suggest the hotter half of the Milky Way may partly represent regions where magnetic fields and cosmic rays interact most intensely. Heat follows invisible pathways. The galaxy's structure guides energy unevenly. Some areas become giant reservoirs of turbulent plasma, while others remain comparatively cool. One remarkable example involves giant radio bubbles discovered overlapping portions of the Fermi bubbles. These radio-emitting structures suggest magnetic fields and cosmic rays extend enormous distances above and below the galactic center. The Milky Way may effectively vent energetic plasma outward through giant magnetized chimneys, and those chimneys likely remain active today, even if the original eruption creating the Fermi bubbles happened millions of years ago. Ongoing star formation and supernova activity near the galactic center continue feeding energy into surrounding magnetic structures. The furnace never fully shuts down, it simply changes intensity over time. Another fascinating possibility involves something called alpha waves. These are magnetic waves travelling through plasma, somewhat analogous to vibrations moving along stretched strings. Cosmic rays interacting with magnetic fields can generate such waves, transferring energy through the interstellar medium over huge distances. In simpler terms, parts of the galaxy may transport heat through giant invisible magnetic vibrations, which sounds wonderfully unreasonable and is nonetheless supported by real plasma physics. The universe often behaves like that. The deeper humans investigate reality, the more it starts sounding like speculative science fiction, accidentally written by mathematicians. Still, despite all this complexity, one broad conclusion has become increasingly clear. The Milky Way is not heated uniformly, because energy itself does not move uniformly. Magnetic fields channel it. Cosmic rays transport it. Plasma redistributes it. Ancient eruptions inject it asymmetrically. And over millions of years, these processes combine into a galaxy where some regions glow with persistent violence, while others drift relatively undisturbed through darkness. The visible stars overhead reveal only a fraction of that activity. Beneath the calm appearance of the night sky lies a hidden electrical ecosystem spanning tens of thousands of light years. Rivers of plasma, storms of cosmic rays, magnetic structures guiding invisible heat through space, and towering above it all, perhaps the clearest evidence yet that the Milky Way once experienced something extraordinary. The giant structures known as the Fermi bubbles. For most of human history, nobody knew they existed. That may be the strangest part. Entire civilizations rose and fell beneath a galaxy containing colossal, hidden structures larger than many smaller galaxies, and absolutely nobody noticed because human eyes were never designed to see them. The night sky looked calm, beautiful, quiet. Meanwhile, towering above and below the Milky Way itself were enormous bubbles of high-energy radiation, stretching across tens of thousands of light years, invisible monuments to something violent. And once astronomers finally discovered them, they changed how scientists thought about our galaxy, almost overnight. Because galaxies are not supposed to casually hide structures that enormous without raising difficult questions afterward. The structures, now called the Fermi bubbles, extend roughly 25,000 light-years above and below the galactic centre. To understand the scale properly, imagine travelling at the speed of light, the fastest speed physically possible according to modern physics. Even then, crossing one bubble from top to bottom would take tens of thousands of years. They are truly gigantic, and yet despite their immense size, they remained hidden until gamma-ray observations from the Fermi Gamma-Ray Space Telescope revealed them in 2010. Gamma rays, you may remember, are among the highest energy forms of light in the universe. They appear in environments involving extreme temperatures, violent particle acceleration, black holes, neutron stars, and powerful cosmic explosions. Ordinary stars do not produce giant gamma-ray bubbles extending across half a galaxy. Something extraordinary had happened near the centre of the Milky Way. And perhaps more importantly for our mystery, whatever created these structures may still be influencing galactic temperatures today. The bubbles are not merely passive clouds drifting harmlessly through space. They contain energetic particles, magnetic fields, and hot plasma. They interact with surrounding halo gas. They continue glowing in gamma rays millions of years after their formation. In a very real sense, the Milky Way may still be recovering from whatever caused them. Now, one reason astronomers became so fascinated by the bubbles is how sharply defined they appear. Their edges are surprisingly crisp. That matters because diffuse gas structures in space usually spread gradually over time. Sharp boundaries suggest something energetic expanded outward rapidly enough to create shock fronts, almost like the blast wave from an enormous explosion. And once scientists began studying the bubbles more carefully, additional clues emerged. X-ray telescopes found huge surrounding regions of hot gas. Radio observations revealed giant magnetic structures intertwined with the bubbles. Microwave observations uncovered the mysterious galactic haze overlapping portions of the same regions. Different wavelengths kept pointing toward the same conclusion. The galactic centre experienced a major energetic event, possibly several, and the effects spread far beyond the visible disk of the Milky Way itself. One especially eerie aspect of the bubbles is their symmetry. They rise above and below the galactic plane almost like gigantic wings or twin pillars extending into intergalactic space. This strongly suggests their origin lies directly in the centre of the galaxy. Something there erupted outward in both directions. And because galactic disks contain dense gas and dust, energy escaping vertically above and below the plane would encounter less resistance than energy trying to push sideways through crowded spiral arms. Imagine steam escaping upward from a crowded city instead of trying to move horizontally through buildings. The bubbles may represent something similar on galactic scales, an ancient release of energy venting into the halo surrounding the Milky Way. Now, scientists still debate exactly what produced them, but broadly speaking, the leading explanations fall into two categories. Either Sagittarius A star, the supermassive black hole at the galactic centre, erupted violently, or massive bursts of star formation generated enough supernova explosions to drive giant outflows into the halo. Possibly both. Let us begin with the black hole explanation because, admittedly giant ancient, black hole eruptions are difficult to ignore once introduced into a conversation. Supermassive black holes often spend long periods relatively quiet before suddenly becoming active when enough material falls inward. As gas spirals toward the event horizon, it heats dramatically due to friction and compression. This process creates accretion disks glowing intensely across multiple wavelengths. In some galaxies, these active black holes produce enormous jets, blasting particles outward near the speed of light. The resulting energy release can reshape entire galactic environments. Astronomers suspect Sagittarius A star may have undergone a smaller version of this process several million years ago. Not enough to transform the Milky Way into a blazing quasar visible across the universe, thankfully, but enough to launch tremendous amounts of energy into surrounding space. Computer simulations show that relatively brief feeding episodes could inflate bubble-like structures remarkably similar to those observed today. Matter falls inward, energy erupts outward, shockwaves expand through surrounding gas, magnetic fields guide plasma into giant lobes. Millions of years later, enormous gamma-ray bubbles remain suspended above the galaxy. The timing fits surprisingly well. Current estimates suggest the bubbles formed somewhere between roughly 2 and 10 million years ago. Cosmically speaking, that is recent. At the time, Earth already contained early human ancestors walking upright beneath African skies. There is something wonderfully unsettling about imagining giant galactic eruptions unfolding while primitive humans learned to shape stone tools. Our species evolved inside a galaxy that may still carry thermal scars from relatively recent cosmic violence, and yet the sky looked peaceful the entire time. Now, the starburst explanation is equally fascinating. The galactic centre contains dense regions capable of producing huge populations of massive stars over short periods. Massive stars live fast and die young as supernovae. If enough form together, their combined stellar winds and explosions could drive enormous galactic outflows upward into the halo. Think of countless overlapping explosions gradually merging into a giant sustained pressure wave. Instead of one sudden eruption, the bubbles would represent the cumulative result of many violent stellar deaths concentrated near the galactic centre. Interestingly, galaxies undergoing intense star formation often display giant outflows very similar to the Fermi bubbles. Astronomers observe such superwinds in other galaxies regularly. These winds carry hot gas, magnetic fields, cosmic rays, and chemically enriched material outward into surrounding space. So once again, the Milky Way begins looking less uniquely calm than humans once assumed. Our galaxy may simply be a quieter version of systems elsewhere in the universe that periodically vent enormous energetic structures into intergalactic space. Still, there are complications. The bubbles contain extremely energetic gamma-ray emitting particles, and explaining exactly how those particles remain energized over millions of years is challenging. Some scientists think shockwaves within the bubbles continuously re-accelerate particles. Others suspect magnetic turbulence helps sustain high-energy populations. There may even be ongoing energy injection from the galactic centre today, albeit at lower levels than during the original event. The bubbles might not be completely fossilized structures. They may still evolve actively. And that possibility becomes very important for understanding the Milky Way's uneven heating, because if the bubbles continue interacting with surrounding gas and magnetic fields, they may help maintain hotter halo regions even now. One particularly fascinating discovery involves giant X-ray arcs surrounding portions of the bubbles. These arcs likely represent shock fronts where expanding material slammed into surrounding halo gas, heating it tremendously. The temperatures involved reach millions of degrees. Again, the gas is extremely diffuse, so this is not ordinary hot in the human sense. But energetically speaking, the halo surrounding the bubbles contains staggering amounts of thermal energy, and notably, those heated regions are not distributed evenly throughout the halo. The bubbles themselves create asymmetry. Some regions become flooded with energetic particles and hot plasma, while neighbouring regions remain comparatively cooler. The Milky Way's temperature imbalance may therefore partly reflect the lingering influence of these giant structures. Another clue comes from polarization measurements. Polarized radio emissions reveal that the bubbles contain highly ordered magnetic fields, extending enormous distances through space. This suggests the outflows responsible for forming them carried magnetized plasma outward from the galactic center. The Milky Way essentially launched giant magnetic structures into its own halo. And magnetic fields matter enormously because they trap and guide cosmic rays. Energetic particles spiraling through these structures continue depositing energy into surrounding plasma. In other words, the bubbles are not merely empty cavities. They function like enormous reservoirs of magnetized energetic particles. The galaxy's hidden heat engine extends far beyond the visible disk itself. One especially intriguing idea proposes that the bubbles help regulate the Milky Way's long-term evolution. Galaxies cannot convert gas into stars indefinitely without feedback processes limiting runaway growth. Outflows driven by black holes or starbursts may help eject gas outward, preventing excessive star formation while redistributing energy into the halo. In simpler terms, galaxies may occasionally need to vent pressure. The Fermi bubbles could represent exactly such a release. An energetic reset mechanism. The Milky Way exhaling, slowly, violently, and on scales difficult for human minds to fully grasp. Now, one detail often overlooked in popular descriptions is that the bubbles are not isolated structures floating separately from the rest of the galaxy. They connect to broader systems of hot gas, magnetic fields, and energetic particle flows extending throughout the inner Milky Way. The galactic center feeds them, galactic winds shape them, halo gas confines them, and surrounding magnetic fields influence how energy spreads through nearby regions. They are integrated parts of the Milky Way's energetic ecosystem, which means their effects likely extend far beyond the visible boundaries astronomers map in gamma rays. Some researchers suspect the bubbles helped redistribute enormous quantities of hot gas throughout the halo. Others think they accelerated cosmic rays that continue influencing galactic heating today. There is even evidence suggesting the bubbles may still be expanding slowly. If true, the ancient eruption has not fully ended at all. Its consequences continue unfolding. Millions of years later, they continue unfolding. The farther scientists study these structures, the more they resemble giant weather systems suspended above the galaxy. Storms made not from water vapor and air pressure, but from plasma, magnetic fields, radiation, and high-energy particles. And like weather systems on Earth, they interact with surrounding environments in complicated ways. Shockwaves compress nearby gas. Magnetic turbulence redistributes energy. Hot plasma rises and mixes gradually into the halo. The bubbles become engines of asymmetry. Some parts of the galaxy remain relatively calm, others continue glowing with the lingering aftermath of ancient violence. There is something oddly comforting about that realization. Not the violent part necessarily, more the idea that galaxies possess histories, scars, echoes. The Milky Way overhead is not frozen in time. It remembers things that happened millions of years ago. Ancient eruptions still shape temperatures and magnetic structures today. The galaxy carries memory and heat, and yet from Earth, the night sky still appears serene. That contrast may be one of the most beautiful aspects of astronomy. Underneath apparent calm lies extraordinary complexity invisible to ordinary sight. Gigantic plasma bubbles tower above the galaxy. Cosmic rays stream through magnetic rivers. ancient shockwaves continue heating halo gas, and humanity sleeps peacefully beneath it all, unaware most nights that our galaxy may once have erupted like a scaled-down version of far more violent galaxies elsewhere in the universe. At first, star formation sounds wonderfully straightforward. A cloud of gas collapses under gravity, grows denser over time, becomes hotter at its centre, and eventually ignites nuclear fusion. A star is born. Light floods outward. Another sun joins the galaxy. Simple enough. Except galaxies rarely allow anything to remain simple for very long, because once astronomers started mapping where stars actually form inside the Milky Way, they discovered something curious. The process is uneven, very uneven. Some regions of the galaxy produce stars actively and almost continuously. Giant molecular clouds collapse into dense stellar nurseries, crowded with newborn suns, massive stars, and turbulent gas. Other regions remain comparatively quiet for immense stretches of time, and importantly for our mystery, the hotter and more violent portions of the Milky Way often overlap strongly with regions where star formation behaves differently. The galaxy is not merely hotter in some places because stars already exist there. It is hotter because stars are born there differently. The conditions themselves vary, and once again, much of that imbalance traces back toward the inner Milky Way. Now, to understand why star formation changes across the galaxy, we need to begin with molecular clouds. These are enormous cold clouds made mostly of hydrogen gas mixed with dust and trace heavier elements. They drift through spiral arms like giant invisible weather systems, sometimes spanning hundreds of light years. Despite their immense size, molecular clouds are surprisingly cold, often only a few dozen degrees above absolute zero. Cold temperatures matter because heat resists collapse. Hot gas expands. Cold gas contracts more easily under gravity. So the coldest regions of molecular clouds become stellar nurseries, where gravity slowly begins pulling material inward. Over time, denser pockets form. Those pockets fragment, and eventually protostars ignite. At least that is the broad picture. In reality, the process becomes chaotic almost immediately. Turbulence ripples through clouds. Magnetic fields resist collapse in some regions while allowing it elsewhere. Shockwaves from nearby supernovae compress gas unpredictably. Stellar winds carve cavities through surrounding material. Star formation resembles weather more than architecture. Messy, dynamic, full of competing forces, and across the Milky Way those forces vary enormously depending on location. Our solar system formed inside one such molecular cloud billions of years ago, in a relatively calm outer region of the galaxy. Compared to the galactic centre, our neighbourhood is spacious and stable. The inner Milky Way is another matter entirely. Near the centre, molecular clouds become denser, more turbulent, and far more energetic. Radiation fields intensify dramatically. Magnetic forces strengthen. Stars crowd together in huge numbers. This changes star formation fundamentally. Astronomers studying the central molecular zone, the dense region surrounding Sagittarius A star, discovered that gas there behaves strangely compared to molecular clouds farther out in the galactic disk. The clouds are hotter, more turbulent, more magnetized, and under far greater pressure. Imagine trying to form delicate snowflakes inside a hurricane. That is somewhat similar to the challenge faced by gas clouds near the galactic center. The environment is restless, and yet, despite those chaotic conditions, massive stars still form there in huge clusters. In fact, the inner galaxy appears especially efficient at producing very massive stars. That matters enormously because massive stars dominate galactic heating. A star 10 times more massive than the Sun does not merely produce 10 times more energy. Stellar luminosity rises dramatically with mass. Very massive stars can outshine the Sun tens of thousands or even hundreds of thousands of times over. And they burn intensely hot. Ultraviolet radiation floods surrounding space. Stellar winds blast material outward at millions of kilometers per hour. Nearby gas clouds become ionized and heated. Then, after only a few million years, the stars explode. The result is a feedback cycle. Dense star-forming regions create massive stars. Massive stars inject enormous energy into surrounding gas. That energy heats nearby environments and stirs turbulence. Turbulence influences future star formation. The cycle continues. Over time, entire regions of the galaxy become thermally transformed by repeated generations of massive stars. And because the inner Milky Way forms stars differently, it develops very different thermal behavior from quieter outer regions. One especially important difference involves star clusters. Near the galactic center, stars often form in huge, dense clusters packed with massive young stars. Some clusters contain hundreds of thousands of stars compressed into relatively small volumes. These environments become energetic beyond ordinary human intuition. Radiation fields overlap intensely. Shockwaves from stellar winds collide continuously. Supernova explosions occur relatively frequently. The surrounding interstellar medium becomes flooded with heat and high-energy particles. In quieter outer regions of the galaxy, star formation tends to occur more gently and diffusely. The contrast becomes dramatic. The Milky Way essentially contains multiple ecological zones for star formation. Some are calm suburbs, others are cosmic industrial districts running continuously at high pressure, and the hotter half of the galaxy strongly overlaps with the latter environments. Now, another major factor shaping star formation is spiral structure itself. The Milky Way's spiral arms are not static solid objects. They are density waves, regions where gas and stars crowd together temporarily as the galaxy rotates. When molecular clouds enter spiral arms, they become compressed. Compression triggers star formation. As stars form, they heat surrounding gas and alter local conditions dramatically. But spiral arms are uneven. Some contain richer gas reservoirs. Some experience more active star formation than others, and because the Milky Way itself is asymmetrical in places, certain large-scale regions accumulate far more energetic stellar activity over time. One fascinating clue comes from observations of giant H2 regions. These are huge clouds of ionized hydrogen surrounding hot young stars. Ultraviolet radiation strips electrons from hydrogen atoms, causing the gas to glow brightly. H2 regions are essentially giant signs announcing recent star formation, and some of the largest and most energetic examples cluster toward the inner galaxy. Astronomers mapping these structures discovered enormous stellar nurseries capable of reshaping nearby environments across hundreds of light years. The galaxy's hottest regions often coincide with these active star-forming complexes. Now, here is where things become especially interesting. Star formation does not merely respond to the environment, it changes the environment permanently. Massive stars enrich surrounding gas with heavy elements through stellar winds and supernova explosions. Those heavy elements alter how gas cools and collapses in future generations of star formation. This creates long-term feedback loops. A region that forms many massive stars becomes chemically different over time. Its gas evolves differently. Its thermal properties shift. Future star formation changes accordingly. The galaxy develops memory through stellar evolution, and once again, the inner Milky Way appears fundamentally distinct from quieter outer regions. The gas near the center contains more heavy elements than much of the outer galaxy. This affects cooling rates, magnetic behavior, and molecular chemistry. In simpler terms, the galactic center has been heavily processed by repeated generations of stars. It has lived a more violent life, and that violent history continues influencing how stars form there today. Astronomers sometimes refer to this as stellar feedback. Young stars inject energy into surrounding gas through radiation and winds. Supernova explosions stir turbulence and drive shockwaves outward. Too much feedback can actually suppress future star formation by blowing gas apart before gravity finishes collapsing it. but under some conditions, feedback compresses neighbouring gas clouds and triggers additional star formation instead. The galaxy becomes self-regulating in complicated ways. Some regions experience runaway bursts of stellar birth, others become temporarily exhausted after violent episodes. And because these processes occur unevenly across the Milky Way, the resulting temperature distribution becomes uneven too. One especially dramatic example involves superbubbles. These are enormous cavities carved into the interstellar medium by overlapping stellar winds and supernova explosions from massive star clusters. Imagine multiple giant stars blasting surrounding gas outward simultaneously for millions of years. The combined effect creates expanding bubbles of hot plasma spanning hundreds or even thousands of light years. Inside these superbubbles, temperatures can reach millions of degrees, and the inner Milky Way contains many such structures. Over time, overlapping superbubbles may merge into giant galactic outflows carrying heat and energetic particles upward into the halo. Some astronomers suspect the Fermi bubbles themselves may partly reflect this process operating on much larger scales. Enough massive stars forming together can reshape portions of an entire galaxy. Now, another important factor involves molecular gas availability. Stars cannot form without raw material. The Milky Way's inner regions contain enormous reservoirs of dense molecular gas compared to many outer regions. More gas means more opportunities for star formation, but it also means more fuel for turbulence, magnetic activity, and energetic feedback. The galactic centre becomes thermally self-amplifying in a sense. Dense gas creates massive stars. Massive stars heat surrounding environments. Hot environments alter future gas dynamics. The cycle continues. And because these energetic processes cluster strongly towards certain regions of the galaxy, large-scale asymmetries emerge naturally over time. One half of the Milky Way may not literally form stars entirely differently from the other half in every respect. But statistically, the distribution of gas density, turbulence, stellar clustering, and energetic feedback varies enough to produce dramatically different galactic environments. Some regions become giant engines of heat and radiation, others remain relatively stable. Another intriguing detail involves the galactic bar. The Milky Way contains a central bar-shaped structure of stars and gas extending outward from the core. This bar influences how gas flows inward through the galaxy. Material gradually funnels toward the centre along the bar, feeding dense inner regions with fresh gas. This process likely contributes significantly to ongoing star formation near the galactic centre. And importantly, gas flows along the bar are not perfectly smooth or symmetrical. Shocks develop, clouds collide, turbulence intensifies. The resulting star formation becomes patchy and uneven. The galaxy effectively channels fuel toward its own energetic core. Some astronomers compare galactic bars loosely to conveyor belts transporting material inward, except these conveyor belts are tens of thousands of light years long and made from stars, gas, gravity, and plasma. Galaxies are wonderfully excessive systems. Now, one especially fascinating realization emerged from computer simulations of galactic evolution. Small asymmetries early in a galaxy's history can become amplified over billions of years. Slightly denser regions form more stars. Those stars inject more energy into surrounding gas. That energy alters future gas flows. Future star formation changes further. Eventually, large-scale differences emerge naturally. The hotter portions of the Milky Way may therefore partly represent the accumulated outcome of billions of years of uneven stellar feedback shaping different regions differently. The galaxy evolved into imbalance gradually, and because galactic processes operate slowly, those imbalances persist for immense timescales. One especially eerie consequence of this involves planetary habitability. Regions near intense star formation experience higher radiation levels and more frequent nearby supernova explosions. Gamma-ray bursts and energetic stellar winds become more common. Life in such environments may struggle. our solar system's relatively quiet location may not be accidental in a broader cosmic sense. Stable environments might simply favour the long-term development of complex life. Meanwhile, closer to the galactic centre, conditions become far harsher. The Milky Way contains neighbourhoods where the sky itself would look dramatically different, brighter, crowded, more dangerous, and significantly hotter in energetic terms. Still, despite all this violence, the galaxy continues forming stars constantly. New suns ignite, old stars explode, gas clouds collapse and disperse, heat flows through magnetic structures and plasma winds. The Milky Way remains alive with change, and the hotter regions continue evolving differently from the calmer outskirts. Which naturally leads toward another major question. Because if massive stars and galactic feedback contribute so much energy into the inner Milky Way, what happens after those stars die? At the exact centre of the Milky Way, hidden behind enormous curtains of dust and crowded star fields, sits something almost impossible to picture properly. Not because it is especially large in physical size, but because it is so dense, so extreme, and so fundamentally strange that ordinary human intuition stops being useful somewhere along the way. Sagittarius A star, the supermassive black hole at the heart of our galaxy. For most of human history, nobody knew it existed. Ancient civilizations mapped the stars overhead, built observatories, tracked planets, and imagined the Milky Way as rivers, pathways, or heavenly smoke, all while a gravitational monster containing 4 million times the mass of the Sun waited invisibly at the centre of it all. Even today, if you look toward the constellation Sagittarius with your naked eyes, you will not see the black hole itself. Thick clouds of interstellar dust block visible light from the galactic centre almost completely. And perhaps that is for the best. Because the environment surrounding Sagittarius A star is not calm. It is crowded with stars moving at incredible speeds, hot plasma spiralling through magnetic fields, radiation flooding outward from energetic gas clouds, and temperatures capable of turning ordinary matter into ionized chaos. The centre of the galaxy behaves less like a peaceful astronomical landmark and more like a giant engine buried under layers of dust and gravity. And many astronomers now suspect this engine may explain a great deal about why parts of the Milky Way are so much hotter than the rest. Now, before going further, it is important to clarify something. Black holes themselves are not cosmic vacuum cleaners endlessly sucking everything inward. This is one of the most persistent misconceptions in astronomy. If the Sun suddenly became a black hole, Earth would not instantly spiral into doom. Our orbit would remain almost exactly the same because gravity depends on mass, not whether something is a star or black hole. The real danger of black holes comes from proximity. Get too close, and gravity becomes overwhelming. Near Sagittarius. A star. Stars orbit at tremendous speeds because the gravitational environment becomes extraordinarily intense near the galactic centre. Astronomers have actually tracked individual stars moving around the invisible black hole over decades. One famous star, called S2, completes an orbit around Sagittarius A star roughly every 16 years. At closest approach, it races through space at over 25 million kilometers per hour. That is not a typo. Entire stars move around the galactic centre faster than most human brains are emotionally prepared to process. And from those orbits, scientists calculated the mass hidden there. Only a supermassive black hole fit the observations. In 2022, the Event Horizon Telescope collaboration even produced the first image of Sagittarius A star itself, or more accurately, the glowing material surrounding its event horizon. The image appeared as a bright ring around a dark centre, a shadow cast by gravity itself. There is something deeply unsettling about seeing a structure where space and time become distorted enough that not even light escapes, and yet, remarkably, Sagittarius A star is considered relatively quiet. Compared to the giant active black holes found in some galaxies, ours is almost sleepy. Some supermassive black holes consume matter so aggressively that they outshine entire galaxies. Their accretion disks blaze with radiation. Jets erupt across millions of light years. Surrounding gas becomes violently energized. Sagittarius A currently behaves much more modestly, at least today, and that phrase matters enormously, because evidence increasingly suggests our galactic black hole was not always this calm. In fact, many astronomers now suspect Sagittarius A underwent periods of much more intense activity in the relatively recent cosmic past. Not billions of years ago, millions, possibly only a few million years ago, which on galactic timescales is surprisingly recent, and if that happened, the consequences may still shape the Milky Way right now. The first clues emerged through X-ray observations. Astronomers noticed giant molecular clouds near the galactic center glowing in X-rays in ways that did not quite make sense. Some clouds appeared to be reflecting echoes of past radiation bursts. Essentially, scientists may have been observing ancient light echoes from energetic events that already ended long ago. Imagine hearing thunder bounce around mountains long after lightning struck. The galaxy may preserve similar echoes through radiation. Those observations hinted that Sagittarius A produced much stronger emissions in the past than it does today. Then came the Fermi bubbles, gigantic gamma-ray structures extending 25,000 light-years above and below the galaxy. The bubbles looked exactly like the sort of thing energetic black hole activity might create. Suddenly, Sagittarius A no longer resembled a permanently dormant object. It started looking like a sleeping giant, one capable of waking occasionally. Now, black holes become active when matter falls toward them. Gas near the galactic center does not orbit perfectly forever. Clouds collide, stars shed material, turbulence redistributes gas. Eventually, some matter loses enough angular momentum to spiral inward. As gas falls toward a black hole, friction and compression heat it tremendously. The infalling material forms an accretion disk glowing intensely across many wavelengths. Ironically, black holes themselves are invisible. The brightest part is often the doomed matter surrounding them, and under the right conditions, those environments become astonishingly energetic. Magnetic fields twist violently, plasma accelerates, jets of particles erupt outward, radiation floods surrounding space. The black hole effectively converts gravitational energy into heat and light with terrifying efficiency. Even a relatively brief feeding episode could inject enormous amounts of energy into the surrounding galaxy. Computer simulations suggest Sagittarius A may have experienced exactly such episodes. Perhaps a giant gas cloud wandered too close. Perhaps disrupted stars supplied additional material. Perhaps starburst activity near the galactic center drove gas inward toward the black hole. Whatever the trigger, the resulting eruption could have inflated the Fermi bubbles while heating surrounding halo gas dramatically. And importantly, such heating would not spread evenly. The galactic disk itself blocks outflows in certain directions. Magnetic fields channel energetic particles asymmetrically. Dense gas clouds redirect plasma flows. The black hole's influence therefore becomes structurally uneven. Some regions receive tremendous energetic input, others remain comparatively sheltered. The hotter half of the Milky Way may partly reflect this ancient asymmetry. Now, one fascinating detail about Sagittarius A is how small it actually appears compared to the galaxy surrounding it. The event horizon itself is tiny on galactic scales, and yet the black hole's influence extends across huge portions of the Milky Way. This happens because black holes do not merely affect nearby matter gravitationally. Their energetic feedback reshapes entire environments. Astronomers now believe supermassive black holes may regulate star formation throughout galaxies. When enough energy erupts outward, gas gets heated and expelled into surrounding halos. Without cool dense gas, future star formation slows down. In this way, black holes help govern galactic evolution itself. the centre controls the whole system partly through energy, and Sagittarius A star appears to have done exactly that at various times in the Milky Way's history. One especially eerie realization emerged from studies of nearby galaxies. Many galaxies contain active nuclei far brighter and more violent than ours. Some shoot giant plasma jets millions of light years into space. Others radiate with such intensity that their central black holes outshine all surrounding stars combined. The Milky Way, compared to these systems, seems tame, but that may simply mean we're observing it during a quieter phase. Galaxies evolve. Black holes cycle between active and dormant states. Sagittarius A star could become more active again someday. Not tomorrow, thankfully. Probably not any time remotely soon from a human perspective. Still, the possibility changes how astronomers think about our galaxy. The Milky Way is not permanently calm. It contains a central engine capable of extraordinary energetic outbursts under the right conditions, and traces of past activity may remain visible all around us. Another clue pointing toward ancient eruptions comes from the temperature of surrounding plasma. The galactic centre contains enormous quantities of diffuse hot gas reaching millions of degrees. Keeping such gas heated over long timescales is difficult. Without ongoing energy input, it should cool gradually through radiation, so something must continue injecting energy into the region. Part of that energy likely comes from massive stars and supernovae, but many astronomers suspect Sagittarius A star contributes significantly as well. Even during relatively quiet periods, small amounts of matter continue falling inward. Magnetic turbulence near the event horizon accelerates particles and produces energetic flares. In fact, Sagittarius A star occasionally brightens dramatically for short periods even today. Astronomers observe sudden bursts of X-rays and infrared radiation, likely caused by hot plasma orbiting near the black hole. The monster sleeps lightly, and even its smaller movements influence surrounding space. One especially interesting feature near the galactic centre involves giant streamers of ionized gas orbiting close to Sagittarius A star. These structures move under the combined influence of gravity, magnetic fields, and turbulence. The environment resembles a storm, not metaphorically, a genuine astrophysical storm of plasma and radiation unfolding around the black hole continuously. Matter spirals inward, energy erupts outward, magnetic fields twist chaotically. The centre of the Milky Way is alive with motion. Now, another reason Sagittarius A star matters for our mystery is timing. If the black hole produced major outbursts within the last few million years, then many hotter galactic structures may not represent stable, long-term conditions at all. They may be temporary aftermath. The galaxy could still be redistributing heat from relatively recent events, hot plasma drifting through the halo, cosmic rays trapped in magnetic fields, shockwaves propagating outward. The Milky Way may still carry the thermal echo of black hole activity long finished. And because galactic processes unfold slowly, these echoes persist for immense timescales. One eruption can shape temperatures for millions of years afterward. There is something strangely beautiful about that. The idea that galaxies remember, not through thoughts or consciousness of course, but through structure, temperature, motion, radiation. Ancient events leave fingerprints across space itself. And Sagittarius A star may be responsible for some of the largest fingerprints in the entire Milky Way. Now, one question naturally arises whenever discussing supermassive black holes. Could Sagittarius A star ever threaten Earth? The comforting answer is no, at least not directly. We are roughly 26,000 light-years away from the galactic centre. That distance protects us enormously. Even major outbursts would dissipate tremendously before reaching our region. In many ways, our location inside the Milky Way appears unusually fortunate, far enough from the dangerous centre to remain stable, close enough to inherit heavy elements produced by earlier generations of stars, positioned in a relatively calm galactic neighbourhood. The universe does not guarantee such arrangements. We simply happen to live in one. Still, the galactic centre continues shaping the Milky Way whether Earth notices or not. Hot plasma flows outward from the inner galaxy. Magnetic structures guide energetic particles across huge distances. Ancient eruptions continue glowing in gamma rays overhead. And deep at the centre, Sagittarius A star waits surrounded by orbiting stars, and swirling plasma like a giant gravitational heart buried beneath layers of dust. Quiet for now, perhaps, but not inactive, not harmless, and certainly not simple. The farther astronomers investigate the hotter regions of the Milky Way, the clearer it becomes that no single process explains them completely. Massive stars contribute heat, supernovae inject energy, cosmic rays flood magnetic structures, ancient eruptions reshape the halo, and at the centre of it all sits a black hole whose past behaviour may still echo through the galaxy today. Of all the strange things humans have discovered about the universe, dark matter may be one of the most unsettling, not because it is violent, not because it glows ominously or destroys planets or lurks dramatically in shadows waiting for heroic astronauts to investigate it. Actually, dark matter is unsettling for a quieter reason. Most of the Milky Way may be made of something we still do not understand. That realization arrived gradually during the 20th century as astronomers began measuring how galaxies rotate. At first, scientists assumed galaxies behaved more or less the way the solar system does. In the solar system, most mass sits in the sun, so planets farther away orbit more slowly. Simple gravity, simple motion. But galaxies refuse to cooperate. Stars near the outer edges of galaxies move much faster than expected. According to visible matter alone, many galaxies should simply fly apart, yet they remained stable. Something invisible appeared to provide additional gravity, and not just a little additional gravity, a tremendous amount. Eventually astronomers concluded that galaxies must be embedded inside enormous halos of unseen matter surrounding visible stars and gas. This invisible component became known as dark matter, and even today, scientists still do not know exactly what it is, which is admittedly a rather extraordinary situation. Humanity mapped the surface of the moon before fully understanding most of the matter holding galaxies together. The universe occasionally enjoys keeping its biggest secrets in plain sight. Now, dark matter earns its name because it does not interact normally with light. It neither emits nor absorbs electromagnetic radiation the way ordinary matter does. You cannot see it directly. Telescopes cannot photograph it normally, and yet its gravity shapes the cosmos on enormous scales. Galaxies rotate because of it. Galaxy clusters remain bound because of it. Large-scale cosmic structure formed partly because of it. The Milky Way itself sits inside a gigantic dark matter halo extending far beyond the visible stars. In fact, the dark matter halo surrounding our galaxy may contain several times more mass than all visible stars, planets, gas and dust combined. There is something wonderfully humbling about that. Human civilization developed under skies dominated gravitationally by invisible material nobody suspected existed until recently. And naturally, once scientists realized dark matter permeated the galaxy, some began asking a fascinating question. Could it also influence galactic temperatures? Could some of the Milky Way's mysterious heating originate from dark matter itself? Now, to be clear, nobody believes dark matter functions like a giant invisible radiator warming the galaxy directly, at least not in any ordinary sense. But certain theoretical possibilities suggest dark matter might occasionally release energy under specific conditions, and if true, the effect could become especially noticeable near the galactic centre, where dark matter densities are thought to be highest. This idea becomes particularly interesting because many unexplained high-energy observations cluster near the centre of the Milky Way. Gamma-ray excesses, unexpected energetic emissions, hot plasma distributions. Some scientists wondered whether at least part of this activity might involve dark matter interactions. The leading concept revolves around annihilation. Certain hypothetical dark matter particles may destroy each other when they collide, converting their mass into energy and ordinary particles. This process would release gamma rays and energetic electrons capable of heating surrounding gas. Now, if that sounds slightly alarming, do not worry. If dark matter, annihilation occurs at all, it appears extremely rare and subtle. The galaxy is not in danger of suddenly exploding because invisible particles became overly enthusiastic one afternoon. Still, over enormous timescales and galactic volumes, even weak interactions might produce detectable effects. And because dark matter density likely increases toward the galactic centre, the inner Milky Way becomes one of the best places to search for such signatures. Astronomers studying gamma-ray observations near Sagittarius A star noticed something curious years ago. An excess of gamma rays appeared near the galactic centre, beyond what some models predicted from ordinary astrophysical sources alone. Immediately excitement followed. Could this be evidence of dark matter annihilation? Possibly. Maybe. Or perhaps not. Astronomy specialises in producing situations where multiple explanations fit observations frustratingly well. The problem is that the galactic centre is already an incredibly messy environment. Massive stars, supernova remnants, cosmic rays, magnetic turbulence, black hole activity, all produce high energy emissions naturally. Separating potential dark matter signals from ordinary astrophysical chaos becomes extremely difficult. Still, the idea remained fascinating enough that enormous research efforts followed. Scientists modelled hypothetical dark matter particles with different masses and interaction properties. They compared predicted gamma-ray patterns to actual observations from the Fermi gamma-ray space telescope and other instruments. Some models matched surprisingly well, others failed completely. The debate continues even today. Now, one reason dark matter heating remains interesting involves how dark matter distributes itself through galaxies. Unlike ordinary gas, dark matter does not collapse into stars or planets because it barely interacts electromagnetically. Instead, it forms diffuse halos surrounding galaxies. Gravity pulls dark matter inwards somewhat toward galactic centres, increasing density there. And if dark matter particles occasionally annihilate or decay, regions with higher density would naturally produce more energetic emissions. This means the galactic centre could experience additional heating compared to outer regions. Not enough to explain everything astronomers observe, but perhaps enough to contribute, and our mystery likely involves multiple overlapping mechanisms rather than one single answer anyway. One especially intriguing possibility involves dark matter spikes near black holes. Theoretical models suggest supermassive black holes like Sagittarius A star might concentrate nearby dark matter into especially dense configurations. If true, interactions near the galactic centre could become enhanced dramatically. In effect, the black hole might help create ideal conditions for rare dark matter processes, which sounds wonderfully unreasonable and yet follows naturally from some gravitational models. The universe often behaves like that. Now, there is another possibility beyond annihilation. Some hypothetical dark matter particles might decay extremely slowly over cosmic timescales, releasing small amounts of energy continuously. If such decay occurs throughout the Milky Way halo, it could help maintain portions of the hot diffuse gas surrounding the galaxy. Remember, astronomers discovered enormous reservoirs of million-degree plasma extending far into the galactic halo. Keeping that gas heated over billions of years is difficult. Ordinary astrophysical sources probably explain most of the energy. But perhaps dark matter contributes a little additional heating quietly in the background, like a tiny invisible furnace operating across cosmic scales. Still, scientists remain cautious here. Extraordinary claims require extraordinary evidence, as the saying goes. And dark matter research exists in a particularly challenging part of science because the subject itself remains invisible. Astronomers infer dark matter through gravitational effects rather than direct observation. That means almost every proposed explanation depends heavily on models, simulations, and indirect evidence. Some apparent dark matter signals later vanish once ordinary astrophysical explanations improve. For example, many researchers now suspect much of the gamma-ray excess near the galactic center may originate from populations of unresolved pulsars instead. Pulsars are rapidly rotating neutron stars emitting intense radiation beams. Large numbers of faint pulsars clustered near the galactic center could collectively mimic dark matter signals surprisingly well. Again, the universe enjoys ambiguity. Still, the possibility remains open enough that scientists continue searching intensely. Because detecting dark matter interactions directly would revolutionize physics entirely. It would reveal the nature of most matter in the galaxy, and perhaps explain previously mysterious energetic structures at the same time. One fascinating aspect of dark matter heating models involves scale. Unlike stars or supernovae, dark matter would influence regions very broadly and diffusely. Its effects would spread throughout halos rather than concentrating solely around visible stellar structures. This might help explain why some portions of the Milky Way halo remain hotter and more energetic than expected, far from ordinary star-forming regions. Again, dark matter likely cannot account for all observed heating. But perhaps it contributes subtly to the larger thermal picture. The Milky Way may be shaped by visible and invisible processes together. Now, there is another reason dark matter matters for our broader mystery, even if it contributes little direct heating. Dark matter shapes the galaxy gravitationally. The Milky Way's enormous invisible halo controls how gas moves, how galaxies merge, and how matter flows over billions of years. This indirectly influences star formation, black hole feeding, supernova distribution, and energetic outflows. In other words, even if dark matter itself does not produce much heat directly, it helps determine where ordinary matter accumulates and where energetic astrophysical processes occur. The visible galaxy exists inside a dark matter framework, and that framework influences everything. Galactic collisions, gas dynamics, halo structure, spiral arm evolution, the motion of stars themselves. Without dark matter, the Milky Way would not look remotely the same. One especially eerie realization emerged from cosmological simulations. Galaxies like ours formed partly because dark matter created gravitational scaffolding early in cosmic history. Ordinary matter later collapsed into those structures, forming stars and galaxies, which means invisible matter shaped the visible universe from the very beginning. Human beings exist because of structures we still cannot fully identify. There is something beautifully strange about that. Now, astronomers searching for dark matter signatures use many approaches simultaneously. Underground detectors attempt to observe rare particle interactions directly. Particle accelerators like CERN search for candidate particles experimentally. Telescopes map gravitational effects across galaxies and galaxy clusters. Gamma-ray observatories monitor regions where dark matter interactions might produce energetic emissions. So far, no definitive answer has emerged. Dark matter remains elusive, and yet its gravitational fingerprints appear everywhere. Some researchers even wonder whether our understanding of gravity itself may require revision, rather than invoking unknown particles. Alternative theories like modified Newtonian dynamics attempt to explain galactic rotation differently. Most cosmologists still favour dark matter overall because it explains many observations remarkably well, but the mystery remains unresolved, which means discussions about dark matter heating inevitably involve uncertainty too. Astronomy is honest about uncertainty more often than people realise. Scientists build models gradually from incomplete evidence. Ideas compete. Observations improve. Old theories fail. New possibilities emerge. And sometimes the universe turns out stranger than expected. Now, regardless of whether dark matter contributes directly to galactic heating, the broader picture remains fascinating. The Milky Way is not simply a collection of stars, it is embedded inside an enormous invisible structure dominating its mass and shaping its evolution. Visible matter drifts through dark gravitational scaffolding, while energetic processes heat different regions unevenly across millions of years. Stars explode, black holes erupt, cosmic rays flood magnetic structures, and somewhere throughout all of it, dark matter silently shapes the galaxy from underneath, invisible, untouchable, yet gravitationally unavoidable. There is something almost poetic about humanity discovering that most of the universe may consist of material we still cannot see properly. Not abstract poetry, thankfully. More the practical sort of realization that arrives quietly when astronomy keeps removing layers of certainty one by one. The night sky appears simple until telescopes reveal hidden radiation. Galaxies appear balanced until heat maps expose asymmetries. Gravity appears understood until stars move too fast. And suddenly the universe grows larger and stranger again. One of the easiest mistakes humans make when thinking about galaxies is imagining them as permanent, fixed, stable, frozen in roughly the same form forever. That impression makes sense because human lives are short. Even entire civilizations pass so quickly compared to cosmic timescales that the Milky Way appears motionless from one generation to the next. The stars overhead look almost identical to how they looked thousands of years ago. Constellations remain familiar. The galactic band still stretches quietly across the sky. Nothing appears to change, and yet the Milky Way is constantly evolving. Not dramatically from day to day, of course. Nobody wakes up and notices the galaxy developed a new spiral arm overnight. But over millions of years, the Milky Way transforms continuously. Gas moves, stars die, new stars ignite, shockwaves expand through interstellar space, black holes feed, magnetic fields shift. Entire regions heat up or cool down depending on what astrophysical processes dominate at the time. The galaxy is not thermally stable at all. It breathes through cycles of energy and cooling spread across immense spans of time, and understanding those cycles helps explain why one half of the Milky Way appears hotter right now, because right now in astronomy can be surprisingly temporary. Now, to begin understanding galactic temperature evolution, we should start with the simplest truth. Heat in space eventually fades. Hot gas radiates energy outward through various forms of electromagnetic radiation. Plasma cools gradually over time. Energetic particles lose energy through collisions and magnetic interactions. Left alone long enough, many hot galactic environments would eventually calm down. But the Milky Way never truly gets left alone. New energy sources constantly appear. Massive stars ignite. Supernovae erupt, galactic winds carry fresh hot plasma into the halo, black hole activity injects radiation and turbulence into surrounding regions. The galaxy operates through overlapping cycles of heating and cooling occurring simultaneously. Some regions cool, while others ignite with new energetic activity. And because these processes unfold unevenly across space, the Milky Way develops shifting thermal landscapes over time. Imagine looking at Earth's weather patterns from orbit over millions of years instead of days. Storm systems would appear and disappear, oceans would shift, continents would move, ice ages would come and go. The Milky Way behaves similarly, except its weather consists of plasma flows, radiation fields, magnetic turbulence, and star formation cycles unfolding across tens of thousands of light years. One especially important cycle involves molecular clouds. Stars form inside cold, dense gas clouds scattered throughout the galaxy. Over time, gravity pulls portions of these clouds inward until protostars ignite. Then the stars begin heating their surroundings immediately. Young massive stars emit enormous ultraviolet radiation capable of ionizing nearby gas clouds into huge glowing H2 regions. Stellar winds blast surrounding material outward at tremendous speeds. Eventually, the most massive stars explode as supernovae. The local environment becomes dramatically hotter and more turbulent, but eventually, after enough energy disperses surrounding gas, star formation slows down again. The region cools gradually, until new molecular clouds accumulate later and the cycle begins once more. Entire sections of the Milky Way pass through these thermal phases repeatedly over hundreds of millions of years. The galaxy is not uniformly old or uniformly active. Different regions exist at different stages of energetic evolution simultaneously. Nowhere is this more obvious than near the galactic center. The inner Milky Way experiences intense cycles of activity because gas continually flows inward through the galactic bar and spiral structures. Dense molecular clouds accumulate near the center, triggering bursts of star formation and feeding Sagittarius A star intermittently. This creates periodic energetic episodes. Massive stars form, supernova rates rise, galactic winds intensify. Perhaps the black hole itself becomes more active temporarily. Then conditions calm somewhat before the cycle repeats later. Astronomers suspect the Fermi bubbles themselves may represent evidence of one such recent active phase. Several million years ago, the galactic center may have entered a much hotter state than today. Huge outflows erupted into the halo. Shockwaves heated surrounding gas. Cosmic rays flooded magnetic structures. The thermal map of the Milky Way shifted dramatically, and even now, millions of years later, some regions may still be cooling from those events. One fascinating aspect of galactic evolution is how slowly heat dissipates in diffuse environments. Here on Earth, hot air cools relatively quickly because our atmosphere is dense. Molecules collide constantly. Heat transfers efficiently. The interstellar medium behaves differently. Gas densities are extremely low. Particles may travel long distances before interacting. As a result, hot plasma in galactic halos can remain heated for astonishingly long periods, millions of years, sometimes longer. The galaxy carries thermal memory. Ancient events continue influencing present temperatures long after the original explosions ended. This helps explain why the Milky Way appears uneven today. The hotter regions may partly reflect relatively recent energetic events, whose effects simply have not dissipated fully yet. The galaxy has not finished relaxing back toward equilibrium, and equilibrium itself may never truly arrive because new energetic events constantly occur. Another major factor shaping long-term temperature evolution involves supernova feedback. Massive stars live briefly but release enormous energy when they die. Supernova shockwaves compress nearby gas clouds, trigger turbulence, and accelerate cosmic rays through surrounding magnetic fields. Clusters of supernovae can merge into giant superbubbles of hot plasma stretching hundreds or thousands of light years. Eventually, these superbubbles break through portions of the galactic disk and vent hot gas upward into the halo. Astronomers sometimes call these structures galactic chimneys. Heat literally escapes upward from the galaxy. Over millions of years, repeated superbubble formation may maintain much of the hot plasma surrounding the Milky Way. And because supernova activity varies across different regions, some portions of the halo receive far more energetic input than others. Again, asymmetry develops naturally. The Milky Way evolves unevenly because its energy sources evolve unevenly. One especially interesting realization from computer simulations is that galaxies may oscillate between more active and less active phases over cosmic time. Gas flows inward gradually through spiral arms and galactic bars. Eventually, enough dense material accumulates near the center to trigger intense star formation or black hole feeding episodes. Energy erupts outward. Gas becomes heated and expelled into the halo. Future star formation temporarily declines. Then over time, fresh gas slowly cools and falls back inward. The cycle repeats. Galaxies may effectively pulse over hundreds of millions of years. not rhythmically in any neat mechanical sense, but through overlapping feedback cycles governing how matter and energy move internally. The hotter half of the Milky Way today may therefore represent a snapshot of one temporary phase within much longer galactic evolution. Given enough time, different regions could eventually become dominant instead. Another crucial factor involves galactic rotation itself. Remember, the Milky Way does not rotate like a solid object. Inner regions orbit faster than outer regions. Stars and gas drift through spiral arms over time. This motion redistributes matter and energy gradually across the galaxy. Gas clouds entering spiral arms become compressed, triggering new star formation. Later, energetic stellar feedback reshapes those regions while the galaxy continues rotating. Heat patterns slowly evolve alongside galactic motion. Even our solar system has travelled through different galactic environments over time. Roughly every 230 million years, the Sun completes one orbit around the galactic centre. During that journey, Earth passes through spiral arms, varying gas densities, and changing radiation environments. The Milky Way surrounding us today is not identical to the one Earth occupied hundreds of millions of years ago, and millions of years from now, conditions will differ again. The galaxy is dynamic on every scale. Now, another long-term influence involves galactic mergers. The Milky Way has absorbed many smaller galaxies throughout its history. Each merger disturbed gas distributions, triggered star formation, and altered thermal structures throughout the halo and disk. Some stellar streams visible today are remnants of galaxies consumed long ago, and the heating effects of such mergers can persist for enormous timescales. When galaxies interact gravitationally, gas clouds collide and compress. Shockwaves propagate through interstellar and intergalactic gas. Starburst episodes ignite. The resulting energetic feedback can reshape galactic temperatures for hundreds of millions of years afterward. Even now, the Milky Way continues interacting with nearby dwarf galaxies. These interactions subtly disturb the halo and may influence future thermal evolution. And eventually, billions of years from now, the Milky Way itself will collide with the Andromeda Galaxy. That future merger will transform both galaxies completely. Star formation rates will surge, gas clouds will collide violently, supermassive black holes may eventually merge, huge energetic outflows will reshape surrounding halos. The Milky Way's current temperature imbalance will become irrelevant compared to the chaos that follows. Fortunately, nobody listening tonight needs immediate plans for galactic collision preparation. The event lies roughly 4 billion years in the future. Still, it highlights an important truth. Galaxies are temporary structures. Their shapes, temperatures, and internal environments evolve continuously over cosmic history. Even the calm-looking Milky Way overhead is merely one phase of a long ongoing transformation. Another fascinating aspect of temperature evolution involves chemical enrichment. Early galaxies contained mostly hydrogen and helium produced after the Big Bang. Heavy elements formed later inside stars and spread outward through supernova explosions. Over billions of years, repeated stellar generations enriched portions of the Milky Way with oxygen, carbon, iron, silicon, and other heavier elements. This changed how gas cools. Heavy elements radiate energy efficiently, allowing enriched gas clouds to lose heat more effectively under certain conditions. As chemical composition evolves, star formation behavior changes too. The galaxy slowly modifies its own thermal properties through stellar evolution. The Milky Way becomes more chemically and thermally complicated over time. One especially eerie implication of all this is that the galaxy we inhabit today may be unusually active compared to some past periods, or unusually calm. Astronomers still reconstructing the Milky Way's detailed evolutionary history cannot yet say with certainty exactly how energetic our current epoch is relative to earlier ages. Perhaps Sagittarius A star once erupted much more frequently. Perhaps starburst episodes dominated the inner galaxy repeatedly. Perhaps the current hotter regions are already fading remnants of a more violent past. The Milky Way's present appearance may simply represent one temporary stage in a long fluctuating history. And because humans observe the galaxy during only an infinitesimally brief moment, we naturally mistake temporary conditions for permanent structure. The hotter half of the galaxy feels stable only because our lifetimes are so short. Given enough time, entirely different regions might dominate. Heat flows, gas circulates, energy redistributes. The Milky Way evolves whether anyone watches or not. One especially beautiful aspect of astronomy is realizing how patient the universe is. Galactic changes unfold slowly enough that stars themselves become markers of time. Ancient supernova remnants continue expanding for millions of years. Hot halo gas drifts gradually through enormous magnetic structures. Nothing rushes. The galaxy can afford patience. And perhaps that patience is part of what makes the Milky Way seem so calm from Earth, despite the violence hidden beneath its surface. The night sky changes too slowly for human eyes to notice, yet beneath that apparent stillness, enormous energetic cycles continue endlessly. Stars are born. Stars die. Black holes feed. Shockwaves travel. Galactic winds rise into the halo. Heat spreads unevenly across the galaxy. And over millions of years, entire thermal landscapes slowly rearrange themselves. One of the strangest things about the Milky Way's hotter regions is that they're not hot in any familiar human way. There are no flames drifting between stars, no burning air, no giant furnaces floating visibly through space. In fact, most of the galaxy is still astonishingly empty, and yet enormous amounts of energy continue moving across it constantly. Heat spreads through the Milky Way, even though there is almost no atmosphere, almost no ordinary conduction, and no oxygen for anything to burn. Which raises a very reasonable question. How does an entire galaxy transport heat at all? On Earth, humans are used to heat moving through contact. A stove warms a pan, sunlight heats pavement, hot air rises through a room. Water transfers warmth efficiently because matter on Earth is relatively dense. But the Milky Way operates under entirely different rules. The gas between stars is so thin that particles may travel huge distances before colliding with anything. In many regions of interstellar space, densities are lower than the best vacuums humans can create in laboratories, and yet galaxies still evolve thermally. Some regions become hotter, others cool. Energy travels enormous distances. The Milky Way contains giant flows of heat despite the emptiness between stars. The secret lies in understanding that heat in space rarely behaves the way humans experience it on Earth. Instead of moving primarily through ordinary contact, galactic heat travels through radiation, plasma motion, magnetic fields, and energetic particles. In a sense, galaxies transport energy more like ecosystems of invisible storms than ordinary physical objects. And once astronomers realized this, many mysteries about the hotter half of the Milky Way started making far more sense. Now, the first major way heat moves through the galaxy is radiation. Stars continuously flood space with electromagnetic energy. Visible light, infrared, ultraviolet, X-rays, gamma rays. All of these forms of radiation carry energy outward through the vacuum. Earth itself survives because of this process. Sunlight crosses 150 million kilometers of empty space before warming our planet. Without radiation, stars would simply glow uselessly into isolation. Instead, radiation spreads energy across entire solar systems and galaxies. Massive stars especially dominate this process. A single large young star can pour enormous ultraviolet radiation into surrounding gas clouds, ionizing and heating them over huge distances. Clusters of such stars create giant glowing H2 regions, where entire clouds become flooded with energetic photons, And because the Milky Way forms massive stars unevenly, radiative heating also becomes uneven. The inner galaxy contains far more intense radiation fields than our quiet local neighbourhood. Near the galactic centre, ultraviolet light, X-rays and infrared radiation overlap continuously from dense stellar populations. The environment itself becomes saturated with energy, but radiation alone does not explain everything. Another major mechanism involves shockwaves. Shockwaves in space behave differently from explosions in Earth's atmosphere because interstellar gas is extremely thin. Even so, when supernovae explode or galactic outflows erupt, pressure waves still travel outward through surrounding plasma, and those shockwaves carry enormous energy. Imagine a giant stellar explosion blasting material outward at thousands of kilometers per second. As the expanding shockwave plows through surrounding gas, it compresses and heats the material dramatically. This process can continue for hundreds of thousands of years. One supernova remnant may expand across dozens or even hundreds of light years, while heating nearby plasma the entire time. Now multiply that process across millions of stars over billions of years. The galaxy becomes full of overlapping thermal disturbances. Some regions contain ancient shockwaves still propagating through space long after the original stars disappeared, and importantly, shockwaves do not spread evenly forever. Dense gas clouds block them. Magnetic fields redirect them. Previous explosions carve low-density channels through surrounding regions. Heat begins flowing preferentially along certain pathways. The Milky Way develops thermal rivers. One especially dramatic example involves galactic winds. Near the galactic centre, overlapping supernovae and stellar winds create enough pressure to drive huge outflows upward into the halo. These winds carry hot plasma, magnetic fields and cosmic rays thousands of light years away from the disk. The galaxy literally exhales heat into surrounding space. And once again, these outflows are not perfectly symmetrical. Some directions allow easier expansion than others. Gas density varies. Magnetic structures channel plasma unevenly. Over millions of years, entire sections of the halo become hotter because they receive stronger energetic flows from the inner galaxy. Now here is where things become particularly strange. A great deal of galactic heat moves not through ordinary gas at all, but through plasma. Plasma behaves differently from normal matter because it is electrically charged. Magnetic fields strongly influence its motion. This means hot plasma does not simply drift randomly outward like smoke in air. It follows magnetic structures, and the Milky Way contains enormous magnetic networks stretching across huge distances. Charged particles spiral along invisible field lines. Energetic plasma becomes trapped in giant loops and filaments. Heat effectively rides along magnetic highways through the galaxy. Some regions accumulate hot plasma because local magnetic fields confine it efficiently. Other regions allow energy to escape more easily. The galaxy's temperature map therefore reflects not only where energy gets produced, but where magnetic structures allow it to travel. This becomes especially important near the Fermi bubbles. The bubbles contain huge magnetic fields intertwined with high-energy particles and plasma. Energetic material likely continues circulating through these structures even now. The Milky Way may contain enormous magnetized convection systems slowly redistributing heat through the halo, not unlike atmospheric circulation on Earth, except operating across tens of thousands of light years. Now, another major heat transport mechanism involves cosmic rays. These energetic particles move near the speed of light through the galaxy. When they collide with gas or interact with magnetic turbulence, they transfer energy into surrounding material. Cosmic rays effectively function like invisible heat carriers, and because magnetic fields guide their paths, they accumulate unevenly across different galactic environments. Some regions become saturated with energetic particles while others remain comparatively calm. The hotter portions of the Milky Way often overlap strongly with regions where cosmic ray densities appear elevated. In fact, astronomers increasingly suspect cosmic rays play a major role in maintaining hot diffuse halo gas surrounding the galaxy. Without continuous energetic input, portions of the halo should cool more efficiently than observations suggest. Cosmic rays may provide part of the missing energy source. One fascinating detail is how slowly these processes unfold. Here on Earth, heat transfer feels immediate because our environment is dense. Touch a stove and energy transfers instantly. The Milky Way operates on astonishingly slower timescales. A supernova shockwave may require millions of years to cross a significant galactic region. Hot plasma drifting through the halo evolves gradually over enormous periods. Cosmic rays wander through magnetic structures for immense spans before escaping. The galaxy redistributes heat patiently, very patiently, and because the timescales are so long, thermal imbalances persist for millions of years. The hotter half of the Milky Way may partly reflect energetic events whose consequences are still spreading slowly outward today. In some regions, the galaxy has not had enough time to cool down yet. Another especially important concept involves thermal conduction. Even in diffuse plasma, heat naturally flows from hotter regions toward cooler ones through particle interactions. But in the Milky Way, magnetic fields dramatically complicate this process. Heat flows more easily along magnetic field lines than across them. Imagine trying to move through a dense forest where paths exist only in certain directions. Energy behaves similarly inside magnetized plasma. As a result, some galactic regions become thermally isolated despite sitting relatively close together spatially. Magnetic geometry shapes how heat spreads. This may help explain why certain hot structures remain sharply defined for surprisingly long periods, instead of diffusing smoothly throughout the galaxy. The Milky Way's magnetic architecture traps heat unevenly. Now, there is another mechanism humans rarely think about when imagining galactic heat: turbulence. The interstellar medium is not calm. Gas clouds collide. Supernovae stir plasma continuously. Magnetic instabilities ripple through halo gas. Galactic rotation stretches and twists structures over time. All this motion creates turbulence across enormous scales, and turbulence itself transports energy. Large turbulent motions gradually break down into smaller motions, transferring kinetic energy into heat. In simpler terms, the galaxy slowly converts chaotic motion into thermal energy. Some astronomers suspect turbulence near the galactic center contributes significantly to heating surrounding molecular clouds beyond what ordinary radiation alone should produce. The inner Milky Way may remain hotter, partly because it is dynamically restless. The galaxy's own internal motion generates heat continuously. Another strange consequence of all this is that some parts of the Milky Way can technically contain extremely hot gas, while remaining almost impossible for humans to feel physically. This confuses many people initially. How can gas millions of degrees hot exist without instantly vaporizing everything nearby? The answer is density. Temperature measures particle motion, not total heat content directly. A tiny number of particles moving incredibly fast can possess very high temperatures while still containing relatively little overall energy. The galactic halo contains plasma hot enough to emit X-rays, yet so diffuse that particles may rarely collide at all. If a human somehow floated through such gas briefly, the danger would come more from radiation exposure than from ordinary burning sensations. Space heat behaves differently from earthly heat, and that difference allows the Milky Way to maintain enormous reservoirs of million-degree plasma across huge regions without resembling an obvious cosmic inferno visually. One especially remarkable discovery involves giant filaments of hot gas stretching through portions of the galactic halo. These structures may represent pathways through which energy flows outward from the galactic center. Astronomers sometimes compare them loosely to circulatory systems. The Milky Way pumps energy through itself, not intentionally of course, but physically. Matter falls inward through gravity. Stars convert mass into radiation. Explosions redistribute energy outward. Galactic winds rise into the halo. Hot plasma circulates gradually back toward the disk over immense timescales. The galaxy behaves like a gigantic thermodynamic machine, and machines rarely distribute heat perfectly evenly. One of the more comforting aspects of this entire subject is how invisible most of it remains from Earth. Human eyes evolved under visible sunlight. We cannot naturally see X-ray plasma bubbles or magnetic filaments glowing in radio wavelengths. If we could, the night sky would look much more chaotic. Great arcs of hot gas would stretch above the galaxy. Shock fronts would glow across supernova remnants. Magnetic structures would thread through the Milky Way. Like giant luminous veins, the galaxy would appear alive with hidden energetic motion. Instead, our limited vision grants the universe a calmer appearance, perhaps mercifully, because galaxies are far stranger than they first seem. The Milky Way overhead looks peaceful largely because humans evolved to see only a narrow slice of reality. Modern astronomy expanded that slice, and what emerged was a galaxy where heat flows continuously, through invisible channels shaped by gravity, plasma, magnetism, and ancient eruptions. No air required, no fire required, just energy moving patiently across enormous distances over millions of years. Milky Way is not a static collection of stars. It is a living environment of moving heat, a giant structure slowly redistributing energy from ancient explosions, stellar births, magnetic storms, and black hole outbursts while humanity drifts quietly along inside one comparatively calm corner of it. Tonight, we began with a simple question. Why is half of the Milky Way hotter than the rest? At first, it sounded almost strange in a comforting sort of way, like one of those curious astronomical details that feels distant enough to remain harmless. A galaxy with uneven temperatures. Interesting, certainly. Maybe even a little mysterious. But the farther we travelled into the Milky Way, the clearer something became. Our galaxy is not calm at all. It only appears calm because we are small, distant, and watching events unfold on timescales far beyond ordinary human experience. The quiet river of stars overhead hides an environment full of turbulence, radiation, magnetic storms, ancient explosions, and gigantic structures carrying heat across tens of thousands of light years. And somehow, humanity evolved right in the middle of it. There is something deeply strange about that realization. Every person who has ever lived existed inside a galaxy already filled with invisible plasma bubbles, cosmic rays, supernova shockwaves, and magnetic fields threading through interstellar space. Ancient civilizations looked upward and saw stillness. Modern astronomy looked deeper and found motion everywhere. The Milky Way never truly rests. Not really. Even now, while Earth turns quietly beneath the night sky, enormous energetic processes continue unfolding all across the galaxy. Somewhere in the spiral arms, cold molecular clouds are collapsing into new stars. Elsewhere, giant suns are nearing the ends of their lives, building heavier elements inside their cores before future explosions scatter those materials across space. Far above the galactic plane, hot plasma drifts through the halo in giant invisible currents. Cosmic rays race through magnetic structures near the speed of light, and deep near the centre of the Milky Way, Sagittarius A star waits in relative silence, after what may once have been a far more violent past. The galaxy appears peaceful only because human lifetimes are too short to watch it changing properly. That may be one of the most important ideas in all of astronomy. Scale changes everything. On human timescales, mountains feel permanent. On geological timescales, continents drift. On galactic timescales, entire thermal landscapes evolve continuously. Heat spreads, gas cools, new stars ignite, ancient shockwaves expand outward for millions of years. The hotter half of the Milky Way exists not because the universe accidentally built our galaxy unevenly one afternoon, but because galaxies are living systems of motion and feedback constantly reshaping themselves through energy. The Milky Way's hotter regions are really records of history, scars left by star formation, traces of black hole eruptions, reservoirs of hot plasma still cooling from ancient violence. The galaxy remembers what happened to it, and it remembers for a very long time. That idea becomes even stranger when you realize how recently some of these events may have occurred. The Fermi bubbles stretching above and below the galaxy may be only a few million years old. Cosmically speaking, that is practically recent news. When those structures possibly formed, early human ancestors already existed on Earth. Primitive humans walked beneath skies containing the aftermath of gigantic galactic eruptions without ever knowing. There is something oddly comforting about that, too. Human beings often feel overwhelmed by the scale of the universe, yet the universe itself carried on quietly around us the entire time, without demanding our attention. The galaxy does not require us to notice it in order to continue evolving. It simply does, patiently, relentlessly, and mostly invisibly. Now, perhaps the most surprising part of this entire story is how much of the Milky Way remains hidden even today. Visible starlight reveals only a tiny fraction of what exists around us. Human eyes cannot naturally see gamma rays from giant plasma bubbles. We cannot detect magnetic fields stretching across the galaxy. We cannot sense hot halo gas glowing in X-rays. We do not feel cosmic rays drifting through Earth's atmosphere every second, and yet all of it surrounds us constantly. The night sky is not empty darkness with stars sprinkled across it. It is layered reality, invisible radiation, ancient shockwaves, magnetic turbulence, moving plasma. The calm appearance of the heavens is partly an illusion created by human biology. Astronomy has gradually peeled back that illusion wavelength by wavelength. Radio telescopes revealed magnetic structures. Infrared observatories uncovered hidden stellar nurseries. X-ray telescopes exposed million-degree gas. Gamma-ray observatories discovered enormous energetic bubbles larger than civilizations could have imagined. Every time humanity learned to see a new kind of light, the universe became more complicated, and somehow more beautiful too, because complexity does not make the Milky Way less wondrous. If anything, it makes it feel more alive. Not alive biologically, of course, but dynamically alive. A galaxy where energy moves continuously through overlapping systems. Stars form and die. Heat flows through invisible magnetic pathways. Black holes influence entire stellar populations. Ancient explosions still shape present temperatures. Nothing truly stands still. Even our own solar system drifts through this environment constantly. Earth orbits the Sun. The Sun orbits the galactic center. The galaxy itself moves through intergalactic space. Everything travels, everything changes, and yet from our perspective beneath the night sky, the Milky Way still appears serene. That contrast may be one of the most beautiful things astronomy offers. The realization that enormous hidden complexity can exist beneath apparent calm. A galaxy may look peaceful while carrying giant scars from ancient eruptions. The universe rarely announces its deepest structures loudly. Instead, they wait patiently for curious minds to uncover them. Now, after everything we explored tonight, the original mystery begins looking less mysterious and more inevitable. Of course, parts of the Milky Way are hotter than others. How could they not be? The galaxy contains dense stellar nurseries, supernova graveyards, magnetic rivers of plasma, ancient outflows from the galactic center, giant cosmic bubbles, and enormous regions flooded with radiation and energetic particles. Different environments produce different thermal histories. Some regions remain relatively quiet for millions of years. Others become energetic crossroads where stars, gravity, plasma, and black holes interact continuously. The Milky Way evolved into imbalance naturally because galaxies are not machines built for symmetry. They are evolving ecosystems of matter and energy. And perhaps that is the most important conclusion of all. The galaxy overhead is not a static backdrop behind human existence. It is an active environment, a moving system, a place where ancient events still echo across space long after the original explosion faded away. Human beings tend to imagine ourselves as living on Earth first and inside the Milky Way second, but astronomically speaking, the opposite may be more true. Earth is one small region inside a vast galactic structure that shapes everything around us. The heavy elements in your body were forged inside ancient stars. The solar system formed from recycled galactic material enriched by earlier explosions. Even the calmness of our local environment may partly result from where we happen to orbit inside the galaxy. We are not separate from the Milky Way. We are one tiny temporary expression of it. And tonight, while you rest here beneath relatively peaceful skies, the galaxy continues its slow, restless motion all around you. Hot plasma drifts invisibly through the halo. Cosmic rays cross interstellar space. Shockwaves expand through old supernova remnants. New stars ignite deep inside cold molecular clouds. The hotter half of the Milky Way still glows with ancient energy, and somewhere near the centre, Sagittarius. A star waits quietly beneath crowded stars and dense clouds of dust, surrounded by the lingering heat of a galaxy that never truly falls asleep, which, in a strange way, makes the quiet of Earth tonight feel even more remarkable.